You think you're watching this video right now. But what if you never existed? The flow of time, the boundaries of space, the memories in your mind, maybe they're all the product of highly advanced software. Scientists have been questioning something for years. Is the universe real? At the quantum level, everything is blurry. Particles may not even exist before you look at them. Time itself is not constant. It slows down as you approach the speed of light and nearly stops when you approach black holes. Could there be a single explanation for all this inconsistency? What if the entire universe is a simulation? In this video, we will explore that unsettling possibility behind time, space, and consciousness. Reality may just be an illusion. Could what we call reality be a simulation of our brains? In light of modern neuroscience and quantum physics, the idea that reality is not objective, but a subjective experience is gaining more support every day. Our brain does not process data from the outside world directly. It does so indirectly by filtering, organizing, and constructing it. For example, our eyes perceive light waves, our ears collect sound waves. However, it is the brain's job to transform these physical signals into an experience of reality. So the world we see, hear, and feel may actually be a virtual reality produced by our minds. The brain does not present a reflection of the external world, but rather a model it has constructed about it. This inevitably leads us to the question, are we experiencing our internal simulation more than external reality? This hypothesis becomes even more striking when combined with simulation theory. If our brain is already processing and interpreting the external world like software, why couldn't a similar system operate at a higher level? Advocates of simulation theory argue that the universe is fundamentally a digital coding system, and that we experience reality through these codes. Just as a character in a computer game believes that everything in their universe is real. We may be conscious beings operating within a larger system. Just as a game engine determines the rules of physics, the universe may have its own game engine in the form of quantum mechanics. This idea is gaining traction with the development of virtual reality technology. Today, with a VR headset, a person can interact with objects that appear physical in a completely artificial world. If our brains can be so easily deceived by external stimuli, is it possible to distinguish reality by trusting our senses? Perhaps we are connected to a highly advanced VR system throughout our entire lives. And the name of that system is consciousness. And maybe we never have the chance to escape from that system. Philosophically, this topic has a long history. Descartes said that our senses can deceive us, stating, "I think, therefore I am," meaning that we cannot be certain of anything outside of our consciousness. Plato's allegory of the cave contains a similar narrative. People are chained in a cave, watching only the shadows reflected on the wall and believing them to be real. If we too believe the shadows to be real, due to our biological limitations, we may never see a higher level of reality beyond the universe we live in. Time is not universal. Could it be a mental illusion? Our belief that time is linear and constant is indispensable to our daily lives. We wake up in the morning and go to sleep at night. Events happen first and then end. However, this straightforward perception has been seriously shaken, especially by Einstein's theory of relativity. When Einstein demonstrated that time is not fixed, but varies depending on speed and mass, the universality of time became a myth. The time of one observer may flow differently from that of another. This suggests that time is not objective, but a variable dependent on the observer. In other words, time is not a fundamental dimension of the universe, but a function of perception. However, the issue is not limited to physics. Research in neuroscience shows that the perception of time is based on the integration of signals processed in the brain. The brain establishes a specific time sequence to process incoming sensory data. However, this sequence is not absolute. Under various experimental conditions, this perception can be altered, adding a completely different dimension to the issue. At the quantum level, the principle of causality loses its clarity. The result of an event can occur before its cause. Time does not have to flow forward here. Quantum superposition means that a particle can exist in multiple states at the same time, challenging the linear flow of time. So, if even the smallest building blocks of the universe do not have a clear direction of time, how real is this thing we call time? Perhaps, as conscious beings, we construct time in order to make sense of events. In conclusion, time may not be a fixed reality that exists outside of us. Perhaps time is a computational system invented by conscious beings to organize their experiences. Just like the sequence of operations in a computer, time is a tool for our brains to make sense of the world. It is not real time, but perceived time. This makes the idea that time is an illusion quite plausible on a scientific and philosophical level. Does quantum entanglement show that reality is not divided? Quantum entanglement is a phenomenon that overturns the rules of classical physics. After two particles interact with each other, they instantly know each other's state, regardless of the distance between them. When you measure one, the result of the other is also determined simultaneously. This demonstrates a form of communication that even exceeds the speed of light. However, this communication does not carry information in the classical sense, as there is no conscious signal. This situation suggests that the particles behave as if they were two ends of the same thing. This leads us to believe that reality is not divided, but holistic. Einstein called this phenomenon spooky action and was disturbed by it. This is because classical physics is based on locality in the universe. The idea that everything can only interact with what is in its immediate vicinity. Quantum entanglement, however, breaks this locality, perhaps at the most fundamental level of the universe. Concepts such as place and distance are meaningless. All particles are part of a large, unified system, and we observe them as if they were separate. In this case, everything that is separate is actually an illusion of a single whole. This holistic structure is often mentioned in mystical teachings, in Eastern philosophies in particular. It is said that the universe consists of a single consciousness and that separations are a mental illusion. Entanglement may be a window that confirms this ancient wisdom through science. If we exist in a structure where everything is connected to everything else, then what we call I may be just a local expression of the system. Thus, individuality becomes an illusion, and wholeness becomes the true nature of the universe. The phenomenon of entanglement may also build a bridge between consciousness and quantum. Some theories suggest that conscious experiences in the human mind also arise from a holistic system like quantum entanglement. These views, which argue that the neurons in our brains are organized at the quantum level rather than the classical level, suggest that the mind and the universe may be parts of a cooperating software. If this is the case, we must first understand ourselves in order to understand the universe. Because in that system, we are not only observers, but also the system itself. Does consciousness operate at the quantum level? Classical neuroscience models attempt to explain consciousness through the brain's synaptic connections, chemical messengers, and electrical circuits. However, these explanations fall short of explaining the most fundamental properties of consciousness. For example, why do some neural activities lead to conscious experience while others do not? Why is conscious awareness not limited to mere information processing? This is where quantum consciousness theories come into play. According to this view, the origin of consciousness should be sought not in classical interactions between neurons, but in quantum processes occurring within the cell's cytoskeleton, known as microtubules. The most well-known proponents of this idea are physicist Roger Penrose and anesthesiologist Stuart Hameroff. Penrose and Hameroff's ORCH, or orchestrated objective reduction theory, proposes that quantum superpositions in microtubules collapse into conscious experience at a certain threshold level. Thus, consciousness is not merely neurophysiological. It is also a quantum cosmological process. This is a highly revolutionary approach because in classical physics, consciousness is viewed as an epiphenomenon or a byproduct. The main criticism of these theories is that quantum effects cannot be sustained in a hot and wet environment such as the brain. However, experiments conducted in recent years have shown that quantum processes can be surprisingly stable in biological systems. In particular, effects such as quantum coherence have been observed in birds' navigation mechanisms, photosynthesis, and certain enzymatic reactions. This raises the possibility that the brain, through evolution's remarkable adaptive capacity, may have developed a complex structure capable of processing information at the quantum level. If consciousness arises at the quantum level, this would transform not only the human mind, but also the way we perceive the entire universe. In that case, consciousness could be a function of the universe rather than the brain. According to this view, consciousness becomes a fundamental component of the universe, just like matter and energy. Perhaps there is a network of consciousness that runs as deeply as time and space in the fabric of reality. The answers to these questions may cause us to rethink not only the brain, but all of existence. Is space an absolute structure or a mental space? Throughout human history, space has been perceived as a fixed backdrop to the observable universe. In Newtonian physics, space is an absolute stage on which events occur. Objects move, change direction, gain speed, and all these processes unfold within this stage. However, Einstein's theory of relativity fundamentally altered this notion of a fixed ground. Now, space is a dynamic fabric that can bend, expand, and ripple along with matter. Mass and energy can warp space. This shows that space is not a fixed, objective structure, but a field shaped by physical processes. But even more radical, some quantum gravity theories suggest that space itself may not be fundamentally real. According to these theories, space is a derivative of information relationships between particles. In other words, space is not a directly observable physical entity. It is a perception arising from interactions between systems. For example, according to the holographic principle, all information in the universe may be encoded on a two-dimensional surface, and our three-dimensional experience of space is a hologram-like projection of this data. In this case, space itself is an illusion, something that appears to exist but does not fundamentally exist. This idea is striking not only in a physical sense, but also in a philosophical sense. If space is not real, then even fundamental concepts such as being there, moving, or changing location may be nothing more than internal arrangements of conscious perception. From a neuroscientific perspective, human spatial perception is a simulation created by the brain. In individuals born blind, the perception of space is derived from the echoes of sound waves or the impact of cane strokes on surfaces. This shows that space is not a visual absolute. It is the mind's way of making sense of the environment. Therefore, space itself may be a construct. If space cannot be defined without conscious experience, it is not possible to speak definitively about its reality. Perhaps space is a platform constructed by the mind to make room for existence. In this case, external space becomes a reflection of an internal intuition. In an unconscious universe, neither being here nor going there is possible. We must therefore consider space not as a fixed reality, but as a coordinate system experienced by conscious beings. Does the measurement problem show that reality is dependent on consciousness? One of the greatest mysteries of quantum mechanics, the measurement problem, has brought about a revolutionary debate in the philosophy of science. According to this problem, before a quantum system is observed, particles exist in multiple states at the same time superposition. However, when an observation is made, this uncertainty collapses, and the system takes on only one state. While the nature of this collapse remains unexplained, some physicists suggest that this process may be connected to the existence of consciousness. Could particles gain reality through the presence of a conscious observer? This hypothesis forms the basis of quantum consciousness. The idea that quantum states can never become real without a conscious observer was first expressed by scientists such as Eugene Wigner and John von Neumann. Eugene Wigner even seriously debated the question: if there is no conscious observer, can the universe exist? This approach argues that reality is dependent on consciousness. In other words, the independent and observer-independent existence of the physical universe is questioned. Perhaps the fundamental structure of the universe consists of probabilities. And what converts these probabilities into reality is consciousness. This idea is dramatically embodied in the Schrödinger's cat experiment. A cat in a closed box can be both dead and alive until the box is opened. However, when the box is opened, that is, when an observation is made, the system collapses into a single state. This situation vividly demonstrates how conscious observation affects reality. If there is no observation, there is no specific reality. In this case, reality can only exist if it is observed by a mind. This view is quite close to idealist philosophy. Philosophers such as Berkeley, who said that to be is to be perceived, expressed ideas that coincide with such quantum theories. If true, reality is not an external phenomenon, but a process that exists together with the mind. Without observation, the universe remains silent, motionless, and potential. Consciousness activates this potential. In this case, the essence of reality is not physics, but awareness. Is reality merely the collapse of probabilities? One of the cornerstones of quantum mechanics, the principle of superposition, states that a particle can exist in multiple possible states at the same time. In this case, at the most fundamental level of the universe, there is not a solid reality, but a jumble of intertwined possibilities. However, when we observe, we experience only one state. So where do the other possibilities go? Do they never happen? Or do they all continue to exist in some way? At this point, the question arises as to whether reality is actually nothing more than the temporary collapse of a cloud of possibilities. If this is the case, the world we observe is only one of the versions that collapses with us. This means that countless alternative realities emerge with every conscious observation. Thus, the continuity of what we call reality is called into question. Perhaps reality is not a fixed structure, but a process that is constantly updated through observation. This turns reality into an event, a temporary and context-dependent state that emerges when observed. This approach challenges the classical notion of objective reality. We do not know what the universe is like without an observer, because we cannot experimentally access it. This feature of quantum theory does not suggest that there is fundamental uncertainty in nature. Rather, it suggests that reality itself is related to consciousness. If observation is a choice, then we are experiencing only one version of reality with that choice. All other possibilities either unfold in other universes or remain unobserved forever. In this case, reality is not something we passively exist in, but something we actively shape. The mind's choices, our observations, and our attention may determine which possibilities materialize. This leads us to the idea that reality is not merely matter, but something that exists together with consciousness. If reality is merely the collapse of possibilities, then the fate of reality is in the hands of the observing mind. Is the universe really an external structure based on our everyday experiences? The universe appears to be outside of us, independent of us, fixed and objective. However, observations at the quantum level deeply shake this assumption. Because if reality comes into being through observation, then the claim that the universe is an external structure rather than an internal one becomes seriously debatable. Some philosophers and physicists argue that the universe is not external, but rather a structure that exists within consciousness. This approach emphasizes the idea that reality does not exist somewhere, but rather arises within awareness. Quantum entanglement is at the center of this debate. Two particles can be connected beyond space-time, and a measurement made on one can instantly affect the other. This shows that there is no classical sense of distance between the particles. Therefore, even the validity of what we call place is questionable. In this context, space may not be an external structure of the universe, but rather a way in which conscious experiences are organized. So, could the universe be a platform for conscious experience rather than a place? Furthermore, some idealist philosophers argue that the universe is not a material structure but a mental one. According to them, the external world is an illusion organized by the mind. Everything we see in our dreams arises from mental activity. It does not require an external source. What if the universe we experience while awake is also a mental structure in a similar way? Then reality would be nothing more than an artificial distinction drawn between the mind and the external world. There is no such thing as outside. Everything is inside. Although this idea may seem radical at first, it has serious parallels with quantum theory. Perhaps we should look for the universe not outside us, but within us. In that case, looking into the depths of our own consciousness is as necessary as looking at the stars to understand the secrets of the universe. Because what we perceive as the external world may actually be a manifestation of consciousness. Does time really flow? Our perception of time seems unchanging in our daily lives. The past has happened, the present exists, and the future has not yet happened. However, modern physics seriously questions this linear understanding. According to Einstein's theory of relativity, time is not a fixed background. For a moving observer, time slows down. In strong gravitational fields, it flows differently. This reveals that time is relative and does not operate in the same way for every entity. So how real is the flow of time in this case? Some physicists believe that time is actually an illusion at the fundamental level of the universe. There are only moments. The sense of flow is an interpretation made by our brains as we recall the past and anticipate the future. From this perspective, the past, present, and future already exist simultaneously. We simply experience the sensation of moving between these moments through a shift in consciousness. The direction of time, or its arrow, is actually defined by the laws of thermodynamics. The increase in entropy creates the impression that time is moving forward. Quantum physicists emphasize that time does not appear in the fundamental physical equations. In Schrödinger's equation or quantum gravity theories, time is not an independent variable. This leads us to believe that time does not exist in the fundamental structure of the universe. Time may be merely an experience, a flow of awareness. The brain may create an illusion of continuity by placing certain signals in a temporal sequence. So in this case, does time really exist, or is it just an order that we experience? If time is an illusion, then the past and the future exist on the same level as the present. This fundamentally challenges concepts such as free will, destiny, and change. Perhaps what we call time is a structure developed by consciousness to make sense of reality by dividing it. In this case, reality is nothing but an infinite now, and time is one of the most complex illusions invented by the mind. Could our minds be creating reality? The world we perceive visually, orally, or tactilely appears concrete and external to us. However, all of this sensory data gains meaning only after being interpreted by our brain. Light is merely photons, but we perceive it as colorful images. Sound is vibrations in the air, but we hear it as music, speech, or nature sounds. In other words, reality is the way the brain interprets signals from the environment. This leads us to question whether there is a reality beyond perception. This approach is known as mental constructivism. Our mind collects data, interprets it, connects it with past experiences, and creates a meaningful world. But what if all of this is only happening inside the brain? What we believe to be real may be a simulation of a neural network. If different signals were sent to our brains, we would experience a completely different reality. In that case, reality is not a fixed structure. It is a model constructed by the mind in the moment, and this model can be different for each individual. Some consciousness studies show that the mind can create reality even without the senses. Deep meditation, hallucinations, dreams, or delusions can produce intense experiences without any external stimuli. This demonstrates the mind's capacity to reproduce reality. The external world may feed our perceptions, but the ultimate experience is always created by the mind. Perhaps the universe itself is an expression of a model constructed in the depths of the mind. If our mind constructs reality, then our sense of certainty about reality is shaken. Because if the mind structure changes, the universe we experience also changes. In this case, it becomes meaningless to speak of an absolute reality. Reality is a fluid structure that is reshaped by the consciousness of each individual. This leads us to the idea that reality is not outside, but inside, in the depths of our minds. Is reality like a dream? The dreams we see in our sleep can be extremely similar to reality. The scenes we see, the events we experience, and even the emotions we feel during a dream are almost indistinguishable from our experiences while awake. However, the moment we wake up, this reality disappears instantly. What if the world we are in right now has a similar structure? Could dreams be a powerful metaphor for understanding the nature of reality? Our brain works during dreams just as it does when we are awake. The visual cortex is active while the logical areas are suppressed. However, the signals come from within, not from outside. This shows that the brain can produce an extremely realistic experience without needing the outside world. If we cannot distinguish between reality and dreams during a dream, could we be falling into a similar illusion in our current state? Perhaps reality is nothing more than a continuous dream. These questions have been debated by many thinkers, from Descartes to Berkeley. According to Berkeley's idealist approach, to exist is to be perceived. Just as everything we perceive in a dream feels real. Everything we perceive while awake could be a similar illusion. There may not be a direct boundary between the consciousness of a dream and waking consciousness. In fact, some advanced meditation techniques produce levels of awareness that merge the states of dreaming and waking. If reality is like a dream, then what does waking up mean? Perhaps waking up from reality means moving to a higher level of consciousness. Or maybe the life we live is just another dream within a dream. In that case, what is real? Perhaps reality is an intertwining of an infinite number of dream layers, and what we call awakening is simply a transition to a higher level. How real is space at the quantum level? In classical physics, space is a fixed and absolute stage in which objects exist. Every object occupies a specific position in this space. However, quantum physics fundamentally changes this perception. The positions of particles are not definite but probabilistic. An electron has a probability of being at a certain point, but this probability is not 100%. Moreover, there are superposition states in which particles can exist in multiple places at the same time. This shows us that space is not as rigid a structure as we think. Quantum entanglement further challenges the concept of space. Even if two particles are billions of kilometers apart, a measurement made on one can instantly affect the other. This effect is faster than the speed of light and invalidates the classical concept of distance. So are these particles really far away? Perhaps the entire universe is a single structure, bound together at a deep level, and space is simply the way we experience this connection. String theories and holographic universe models also suggest that space is actually a secondary dimension. True information is encoded on the surface of space. We experience it as if we were living in the depths of this surface. These approaches argue that space is not real like matter. It is one of the organizing forms of consciousness. Thus, place and distance may not be fundamental components of reality. They could be artificial distinctions of experience. If space is merely an illusion at the quantum level, then physical separations largely lose their meaning. Perhaps everything is actually different focal points of the same plane of consciousness. Our bodies, stars, galaxies all are temporary forms within this universal consciousness, and space is not what separates them, but a map of consciousness that connects them. Could consciousness be the fundamental building block of the universe? Consciousness has long been seen as merely a complex product of biological systems. However, with quantum mechanics, this view is gradually changing. This is because the universe does not operate in a deterministic manner as predicted by classical physics, but is shaped by uncertainty and the observer effect. If it is thought that reality does not take on a specific form without an observer, that is, consciousness, then consciousness is not merely something that arises in the universe, but perhaps something that constitutes the universe itself. In this case, could consciousness be the first principle that defines matter rather than matter creating it? Some philosophical approaches, such as panpsychism, argue that there is a kind of mentalism in all of nature. According to this view, even stones, trees, planets, and atoms contain a simple form of consciousness. This consciousness is a kind of internal experience that is different from ours, but lies at the foundation of the universe. If this is true, then consciousness is not a temporary phenomenon that emerged later in the universe. It is the building block of everything. In other words, just like space, time, and energy, consciousness is an integral component of existence. This idea gains further strength as quantum theory demonstrates that the observer affects reality. Without observation, the wave function does not collapse. Physical reality does not exist. At this point, conscious beings are thought to have not only an observational role in the universe, but also a creative one. This brings to mind the idea that the universe is shaped within a sea of consciousness. Perhaps there is an invisible network of mindfulness operating behind matter, and this network weaves together the stars, the planets, and us. If consciousness is the building block of the universe, this would be a modern confirmation of an ancient truth, debated not only by physicists, but also by philosophers and spiritual traditions. From Vedanta to Buddhism, from Hermetic traditions to Kabbalistic teachings, many ancient systems define consciousness as the essence of the universe. Now, science seems to be confirming this ancient intuition. Reality may be a stage that exists with consciousness. Therefore, to understand the stage, we must look not only at matter, but also at inner awareness. Could the universe be a simulation? The numerical structure of the universe and its mathematically explainable nature have surprised some scientists. This is because the laws of nature seem to work like computer codes. Everything can be expressed with formulas, equations, and constants. This has led some researchers to suggest that the universe may actually be a gigantic simulation. If everything can be coded, then perhaps this universe is a digital system that runs on codes. This idea is known as the simulation hypothesis and has become a theory that is increasingly taken seriously. With the advancement of computer technology, we are now able to create our own small universes. The systems we create in video games, virtual reality, or artificial intelligence environments can produce situations similar to the experiences of conscious beings living within them. Now, imagine if a civilization billions of years more advanced than ours had created a simulation of the universe with millions of times the sensitivity of our own. Would the conscious beings within it be able to tell the difference? Perhaps we are already in such a simulation, and it is impossible for us to know. Some properties of quantum physics support this idea. In particular, the collapse of the wave function, that is. The system taking on a specific state only when observed is likened to programming that saves processing power. Just as images load when we look at a screen, unobserved regions of the universe may be kept outside the scope of processing. This suggests that the universe functions like software that optimizes its resources. What if what we perceive as reality is merely a sequence of processes, a rendering result? If this is true, the boundaries of reality are much more flexible than we think. The laws of physics that we accept as real may be nothing more than the programming language of the simulation. Death may be a system shutdown. Time may be a data stream organized according to the order of processes. In this case, the idea of reality is turned upside down. What we believe to be real may have been designed by a consciousness in another dimension. Perhaps we are beings trying to reconnect with that consciousness. Does the moment of measurement create reality? One of the most mysterious principles of quantum physics is that particles do not exist in a specific location or state before they are measured. In other words, an electron is both here and there until it is measured. However, at the moment of measurement, when the system interacts with the observer, the electron collapses into a specific position. This collapse is defined as the moment when the observer interacts with the universe and fixes reality. So does reality begin with measurement. Is there really anything there when no measurement is made? This question creates a fundamental philosophical crisis in the quantum world. According to classical thought, the universe exists whether it is observed or not. But quantum mechanics directly challenges this assumption. If no measurement is made, the system remains in a wave function state. This opens up the concept of objective reality for debate. Perhaps the universe only becomes real when it is observed by a consciousness. This suggests that the human mind directly influences the existence of the universe. Many experiments, especially the double-slit experiment, clearly demonstrate this paradox. Electrons behave like waves when they are not observed, but behave like particles when observation begins. It is as if conscious awareness determines how the universe behaves. This suggests that reality is not passive, but actively created. Perhaps every measurement, every observation, every focus of attention creates a new moment in the universe. Reality is a stream that is constantly updated through these observations. If this is true, then we are not observers of reality, but its creators. The observing consciousness gives birth to a new state of the universe with every measurement. In this case, even the past is not fixed. It can become a structure that is reconstructed with measurement. The future, on the other hand, already exists as an infinite possibility. Reality is not rigid. It is a dynamic structure that dances with consciousness. Can time be merely a perception of consciousness? In everyday life, time appears to be a fixed and directed flow. The past has been lived. We are in the present, and the future has not yet come. However, the linear nature of time in the physical universe is being questioned. Einstein's theory of relativity showed that time is not fixed. It can change depending on speed and mass. In fact, if we move fast enough, time can slow down for us. This reveals that time is not a universal reality, but a perception that varies depending on the observer. Perhaps time is not objective, but the mind's way of organizing reality. Consciousness itself works by fragmenting time. Our memory creates the past, our attention experiences the present, and our imagination constructs the future. However, all these layers are products of the mind. Some advanced meditation techniques or hallucinogenic experiences radically alter the perception of time. A second can feel like hours, or hours can feel like a moment. This shows that time is not objective and changes according to the level of consciousness. Perhaps time is an experience constructed by consciousness, like a film strip, and the universe itself is timeless. In physics, the block universe model argues that all time past, present, and future already exists. Our movement in time is like tracing a path in this block universe. As the mind moves between these blocks, it creates the experience of now. However, in reality, all events may exist at the same time. In that case, time does not flow. We flow within time with consciousness. In this case, time is not the flow of the universe, but the flow of the mind. Perhaps the past and the future are merely mental projections of the present. If time is merely a product of consciousness, then concepts such as death, aging, and history must also be re-examined. Because these are products of the timeline, but if that timeline only exists with the mind, then perhaps there is a state of consciousness that exists outside of time. This is defined in mystical teachings as going beyond time, and science may slowly be confirming this possibility. Reality may not be temporal. It may be a structure of consciousness beyond time. Could space be a projection of consciousness? We think of space as a three-dimensional stage where everything around us exists. Objects, distances, directions, all of these occupy a place in this spatial order. However, at the quantum level, nothing is exactly where it is. The positions of particles are uncertain. Entanglement renders the concept of distance meaningless. So, does space really exist? Or could it also be a projection created by consciousness to make sense of the external world? The brain organizes sensory data into a spatial model. It interprets the direction of sound, the angle of light, the size, depth, and movement of objects according to this model. But we can never know whether this model is an exact representation of reality. Perhaps our mind presents us with a spatial order that does not actually exist as real. Dreams clearly demonstrate this. In dreams, we also have a sense of space. But this is only a mental simulation. Neuroscience, especially virtual reality studies, supports this idea. When the right signals are sent to the brain, we believe we are in a non-existent environment. The body is not there, but the mind reacts as if it were. This shows that space is not external, but an internal experience. The external world is projected onto a mental screen, and we call this space. However, this may simply be a mapping mechanism of consciousness. If space is a projection of consciousness, then the difference between here and there is also an illusion. Everything may exist on the same plane of consciousness. We simply perceive different points on this plane as separate. This gives us a sense of separation rather than a sense of wholeness. However, reality may be a single ocean of consciousness without space. And we, like waves in this ocean, experience only momentary illusions of space. Does quantum uncertainty indicate that reality is random? In classical physics, the universe works like a clock. Everything can be explained by cause and effect, and the future can be predicted with accurate formulas. But in the quantum world, things are completely different. A particle's location is not definite. We can only talk in terms of probabilities. This leads us to think that reality is not a specific thing, but a cloud of infinite possibilities. When we observe it, this cloud collapses, and a single result emerges. Some physicists interpret this as the fundamental structure of the universe being probabilistic. In other words, the universe, like a die, may be producing new results every moment. If this randomness is at the center of everything, the idea of determinism collapses. No matter what the past was, the future cannot be determined with certainty. This leads us to reevaluate concepts such as free will, fate, and coincidence in a new light. Reality is not a pre-written script. It is a poem that is reborn every moment. And perhaps the author of this poem is consciousness. Because with conscious observation, the quantum system chooses a state. Things that appear random may actually be possibilities that resonate with our level of consciousness. Perhaps the universe is not completely random, but operates in a complex order that is beyond our comprehension. Within that complexity, we as conscious beings choose our own reality or are drawn to it. Could reality be just a state of consciousness? We think that what we call the external world exists independently of the perceptions of the mind. However, this assumption is fundamentally questionable because everything we perceive with our senses, colors, smells, sounds, surfaces, is actually just our brain's interpretation of external stimuli. Light frequencies strike the eye, are converted into electrical signals, and the brain perceives them as red. But is that red really there? Or is it merely a mental construct? The answer to this question implies that reality may be a subjective state of consciousness rather than an objective reality. In philosophy, this approach is known as idealism. Philosophers like Berkeley argued that reality exists only in the mind, and that an objective reality independent of the external world can never be observed. Because no matter how careful we are, we experience everything only through our minds. This suggests that the universe is not outside us, but inside us. In other words, what we call reality may be a manifestation of our level of consciousness. Modern quantum theory also indirectly supports this idea. This is because without an observer, the state of the system is not certain. Reality comes into being with observation. If there is no observer, the wave function does not collapse. That is, reality does not become apparent. In this case, consciousness becomes not only a perceiving element, but also a creating element. From this perspective, each individual may be creating their own reality. Reality is an infinite interpretation of a collective field of consciousness. If reality is merely a state of consciousness, then the material world may be nothing more than a concentrated form of that consciousness, just like a table in a dream. It can be touched and felt, but it is gone when you wake up. In this case, everything we see in the universe is a form of consciousness, just like a dream. And we exist within that form, together with it. Reality is not something external. It is us. Our awareness is at its center. Does quantum entanglement invalidate space and time? Quantum entanglement is the connection between two particles, such that an effect on one instantly affects the other, no matter how far apart they are. Even if one particle is at one end of a galaxy and the other at the other end, when one is measured, the other instantly enters a specific state. This effect is so fast that it appears to occur even before the speed of light. This suggests that space and time are not absolute. Perhaps there is no distance between the particles. They are two sides of a single thing whose unity has been broken. Einstein initially described this idea as spooky action at a distance and found it unsettling. This is because his physics stated that no information could be transmitted faster than light. However, experiments have clearly shown that entanglement is real, and that the rules of classical physics do not apply here. This challenges our understanding of reality. This is because we are talking about a connection that is not separated by space or time. It is as if the particles are not in different places, but on the same plane of consciousness. Some physicists suggest that there is a deeper structure behind quantum entanglement. This understanding of unity affects not only physics, but also spiritual teachings. Because in Eastern mysticism, the idea that everything is one has been expressed for centuries. Quantum entanglement may be scientifically confirming this ancient intuition. If everything is connected, then every event, every consciousness, every particle in the universe is fed from a common source. And we do not yet know this source. Does the universe exist as it is observed? With the double-slit experiment, the scientific world realized that the behavior of particles changes depending on whether they are observed or not. When not observed, particles behave like waves. They exist in a state of probability, able to be in multiple places at once. However, when an observation device is placed, the system collapses, and the particle appears at a single point. This raises the question, does the universe only exist when observed? If there is no observation, does existence cease? This question is revolutionary in both physics and philosophy. Until now, we believed that the universe existed independently of us. But quantum experiments reveal that consciousness is directly related to the state of existence of the universe. Perhaps reality is a flexible structure that constantly changes according to the observer. When there is no observation, the universe is a sea of possibilities. When observation begins, a reality island emerges from this sea. Some theorists explain this situation with the idea of a participatory universe. According to this, we do not merely perceive the universe, we also create it. The observer plays an active role in the creation of the universe. This brings with it a huge responsibility at the cosmic level. With our observation, we choose a state of the universe and bring it into existence. In this case, reality is not a static structure. It is a constantly recreated process. If there is observation, there is reality. If there is no observation, there is only potential. This is a revolutionary understanding, both scientifically and spiritually, because this idea shows that the universe is not an unconscious machine, but that consciousness is at its center. Perhaps the universe is like a book that opens as we watch it. As we turn the pages, the content appears. When we are not there, the book is just empty potential. Is there a connection between consciousness and quantum processes? The relationship between quantum physics and consciousness is one of the most controversial and intriguing topics of our time. Some theorists believe that quantum processes occurring in our brains form the basis of consciousness. This is because classical physics falls short in explaining the experience of consciousness. Consciousness is not simply a collection of electrical signals, but something much more complex and subtle. The uncertainty and probabilities of quantum mechanics may overlap with free will, creativity, and intuitive moments in consciousness. Roger Penrose and Stuart Hameroff's orchestrated objective reduction ORC. OR theory suggests that consciousness arises from quantum processes in microtubules. According to this theory, the sudden collapse of quantum states triggers the brain's electrical activity and creates the experience of consciousness. This suggests that consciousness is not merely a biological or chemical process, but is deeply rooted in a quantum-level reality. If this is true, consciousness could serve as a bridge between matter and energy. This connection also revisits the philosophical mind-body problem, because the nature of quantum processes involves probabilities rather than certainty. Consciousness may create experience by selecting from this sea of possibilities. This suggests that conscious beings are active elements in the universe, interacting with it. In other words, consciousness is not a passive observer, but a creative force in the universe. Finally, this theory opens new doors in the quest to understand ourselves and the universe. If consciousness is connected to quantum processes, questions such as the meaning of life, the origin of existence, and universal consciousness bridge the gap between science and spirituality. This is a massive paradigm shift that could completely alter our perception of reality. Could parallel universes and multiple realities be possible? One of the most intriguing implications of quantum mechanics is the idea that the universe may not consist of a single reality, but rather a collection of parallel possibilities known as multiple universes. The many worlds interpretation states that every quantum measurement actually causes the universe to split into multiple wave functions, each of which exists in a different reality. This means that there are countless other universes alongside the one we experience. This theory solves the problem of randomness and uncertainty because one possibility is not chosen. All of them occur. We are just living in one branch. However, in another universe, we may be making different decisions and living different lives at the same time. This fundamentally challenges traditional understandings of fate and free will. This separation between universes gives consciousness a new meaning. Consciousnesses in different universes have different experiences. The idea of parallel universes is not just science fiction. It is a serious scientific hypothesis. Physicists are searching for traces of these universes in the cosmic microwave background or in the behavior of quantum computers. Although no definitive proof has been found yet, it is a mathematically consistent theory that aligns with the laws of physics. This makes the existence of multiple realities possible. If parallel universes truly exist, this would radically expand our understanding of reality, because reality is not fixed or singular. It could be multi-layered and infinitely diverse. Our consciousness has chosen a place within these universes and experiences life there. Perhaps what we call death is simply the gateway to another parallel universe for consciousness. Why could the linear flow of time be an illusion in our daily experience? Time always flows forward. However, in physical reality, time does not necessarily have to be linear. Einstein's theory of relativity showed that time changes depending on speed, mass, and gravity. Quantum physics further stretches the concept of time. In some theories, time is not linear but wavy or cyclical. This suggests that time may be a perceptual illusion. Neuroscientific studies also reveal that the perception of time is created in the brain. The brain organizes complex information from the outside world to create perceptions of the past, present, and future. This process is like a simulation that consciousness uses to make sense of the world. The flow of time is part of this simulation. The bending, speeding up, or slowing down of time in dreams and hallucinations demonstrates the flexibility of this perception. Philosophically, many teachings argue that time is not linear. Time may actually be an infinite repetition of a single moment. Now, or different reflections of a whole. The past and future are mechanisms of memory and expectation within consciousness. They do not exist in reality, but within the mind. Thus, time is nothing more than a useful structure created for consciousness. If time is not linear, this requires us to rethink concepts such as death, aging, and destiny. Perhaps time is an illusion that moves within consciousness, not within the universe. This shows us that life, death, and existence have a much more flexible and mystical nature. A reality beyond time is possible. Does quantum uncertainty mean that there is randomness at the heart of reality? Heisenberg's uncertainty principle states that the position and momentum of a particle cannot be known with certainty at the same time. This means that the universe is based on probability and randomness, not certainty. Matter and energy move within uncertainties rather than definite rules. This undermines the classical understanding of determinism and shows that there are uncontrollable, spontaneous events at the core of reality. This randomness supports the idea that free will can exist in the physical world. If the laws of nature were definite and unchanging, everything would be predetermined. However, thanks to quantum uncertainty, the universe becomes a constantly renewing structure, full of surprises. This allows consciousness to be an active and creative element. Perhaps free will arises from this uncertainty. From a philosophical perspective, this challenges the deterministic worldview. Reality is not a rigid set of cause and effect relationships, but rather a complex web of possibilities. This means that humans and the universe are in a constant state of open-endedness. From this perspective, the universe is not a mechanism, but a living, changing organism. Quantum uncertainty also shows that the universe is constantly in a state of formation. Nothing is completely certain. New possibilities open up every moment. This reveals that reality is not static, but dynamic and alive. Perhaps we are conscious travelers navigating this sea of infinite possibilities. Is it possible for consciousness to transcend time? Can consciousness exist beyond time in everyday experience? Consciousness is bound to time. We remember the past and plan for the future. However, some experiences suggest that consciousness can transcend the boundaries of time. Phenomena such as déjà vu or premonitions suggest that the mind can operate outside the linear structure of time. Meditation and mystical experiences, on the other hand, give the sensation of consciousness traveling through time or stopping the flow of time. In quantum theories, since time does not have an absolute existence, Consciousness can also be considered independent of time. Consciousness may be an entity that experiences the past, present, and future all at once. In this case, consciousness moves not within time, but in a dimension beyond time. Some physicists are exploring quantum entanglement and quantum information theory to explain this ability of consciousness. Consciousness that exists beyond temporal limitations also opens up the possibility of life after death. Because where time ends, consciousness can continue. The concepts of an eternal soul and infinite consciousness in spiritual traditions also align with this scientific perspective. If consciousness can transcend time, our understanding of life and death would change radically. Such timeless consciousness experiences deepen the meaning of human existence. This is because consciousness is not merely a product of the body and brain activity. It may exist at a level of reality independent of time. This allows for a broader connection with the universe and all beings. How can the relationship between mind and matter be explained by quantum theory? The mind-matter problem is one of the oldest and most complex questions in philosophy. It is difficult to explain how conscious experiences arise from the activities of the physical brain. Quantum theory opens new doors in this regard. This is because quantum processes are different from classical physics. Concepts such as wave-particle duality and superposition blur the boundaries between mind and matter. Theories such as or suggest that quantum processes are at the foundation of the mind. According to this view, the mind is not merely a biochemical system, but a phenomenon at the quantum level. Thus, the mind may possess certain properties that interact directly with matter, but are independent of it. This raises the possibility that the mind exists beyond the physical world. This relationship suggests that consciousness is a universal and fundamental force. Matter may be a tool shaped by consciousness and within which consciousness moves. In this case, reality is seen as the product of the interaction between mind and matter. This understanding shows that mind and matter are not separate, but parts of a whole. In conclusion, quantum theory offers a powerful tool for reinterpreting the mind-matter duality. Consciousness is not merely the result of neural activity in the brain. It is a reality intertwined with quantum processes and tied to the fundamental structure of the universe. This could revolutionize our understanding of human existence and the nature of the universe. How does quantum entanglement affect reality? Quantum entanglement is the phenomenon where two or more particles remain instantly connected to each other, regardless of the distance between them. This phenomenon cannot be explained by classical physics because information cannot travel faster than the speed of light. Entanglement challenges the principle of locality in reality and suggests that there is a fundamental interconnectedness at the core of the universe. This indicates that particles are not independent, but rather parts of a whole. In this context, the idea emerges that the universe is interconnected like a network and that its parts cannot be separated from one another. Quantum entanglement suggests that consciousness may also be part of this network. Perhaps communication between consciousnesses occurs through this entanglement and transcends the boundaries of time and space. Thus, reality is not fragmented, but based on a continuous unity. The fact that entanglement can affect reality in this way presents a model of the universe that is very different from what we perceive in our daily experiences. Information and interaction are not limited to physical contact. Everything may be connected through universal consciousness or quantum fields. This allows mystical and philosophical teachings to gain a scientific foundation. In conclusion, quantum entanglement demonstrates that there is an invisible and instantaneous connection between particles at the core of reality. This leads us to view the universe not as a mechanical machine, but as a living, conscious whole. Therefore, Reality is far more complex and mysterious than what we perceive. Could the universe be a hologram? The holographic universe theory suggests that our universe is not a three-dimensional reflection, but rather a hologram composed of a two-dimensional information field. This idea emerged from studies on black hole thermodynamics and quantum gravity. If true, our entire universe is a projection composed of information encoded at its boundaries. This theory completely changes our perception of reality, because space, time, and matter are fundamentally structures composed of information and mathematical codes. We live within the holographic reflections created by this information. Reality could be more of an information-based simulation than a physical experience. The holographic universe model also offers different perspectives on the nature of consciousness. Consciousness can be thought of as a structure that decodes and experiences this holographic information. In other words, consciousness could be the interface of the universe's fundamental computer program. This perspective supports the idea that the universe is a simulation and questions the meaning of existence. Ultimately, the holographic nature of the universe redefines the fundamental structure of reality. The physical world we experience is a reflection of a deeper level of information. This blurs the boundaries between reality and consciousness. 30. What is the difference between quantum reality and classical reality? Classical reality is a world where objects have specific locations, speeds, and properties, and cause and effect relationships are definite. Our daily lives and the macroscopic world operate according to these rules. However, quantum reality is the microscopic level where particles are defined by wave functions and properties such as superposition, entanglement, and uncertainty apply. In quantum reality, particles can exist in multiple states simultaneously, but collapse into a specific state upon observation, becoming classical. This means that reality can change depending on the observer. In other words, reality is shaped by the influence of the observer's consciousness. While classical reality is fixed and objective, quantum reality is filled with probabilities. This difference suggests that the universe may have a two-layered structure. While the macroscopic world operates with determinism and certainty, the microscopic world contains probabilities and uncertainties. This fundamentally alters our perception of reality and brings the role of consciousness to the forefront. Ultimately, this distinction between quantum and classical reality shows that the universe has both a definite and a flexible structure. Consciousness may be the key that bridges these two realities. How does quantum superposition affect reality? Quantum superposition is the ability of a particle to exist in multiple states at the same time. This contradicts the laws of classical physics because such a possibility is not observed in macroscopic objects. However, at the microscopic level, particles carry multiple possible states simultaneously in the form of a wave function. And these states cannot be resolved until a measurement is made. This situation suggests that reality is based on probability rather than certainty. In our daily lives, we see a single outcome. But in the quantum world, multiple possibilities of reality can exist simultaneously. This provides an important clue to understanding the multi-layered and complex structure of the universe. Superposition also raises new questions about how consciousness experiences reality. Consciousness may select among these possibilities to create a specific experience. From this perspective, consciousness is seen as an active process that shapes reality. In other words, reality may not be a passive environment, but a structure that interacts with consciousness. Finally, while the effects of superposition on everyday life are still debated, this phenomenon forms the basis of quantum computers. In the future, the power of superposition could revolutionize technology and information processing. Thus, Thus, the relationship between reality and consciousness could become even more profound. Quantum tunneling and the limits of reality. Quantum tunneling is the phenomenon where particles can overcome energy barriers that they should not be able to pass through according to classical physics. This shows that the rigid boundaries of reality may be more flexible than we think. In the quantum world, particles can sometimes make transitions that seem impossible. This phenomenon suggests that the physical boundaries of the universe may be different from our perception. Perhaps there are no fixed walls between time, space, and matter. Quantum tunneling may open new doors in the interaction between consciousness and matter. The mind may transcend physical boundaries. From a technological perspective, tunneling forms the basis of modern electronic devices and quantum computers. This phenomenon, which pushes the boundaries of reality, plays a critical role in our understanding of the universe's potential. Perhaps consciousness provides access to different realities through these tunnels. Ultimately, quantum tunneling not only limits reality, it also expands it. The universe is a structure that stretches and reshapes its boundaries, and consciousness may be at the center of this process. Can quantum computers change our perception of reality? Quantum computers, unlike classical computers, use quantum qubits. These qubits can perform highly complex calculations simultaneously thanks to superposition and entanglement. This technology has the potential to revolutionize information processing and profoundly impact our understanding of reality. Quantum computers can provide new insights into the fundamental workings of the universe by simulating complex quantum systems. This could help us better understand the nature of concepts such as consciousness, time, and space. Additionally, quantum simulations allow us to experimentally test the fundamental structure of reality. Furthermore, quantum computers open new horizons in artificial intelligence and consciousness research. Solving the relationship between consciousness and quantum-based processes becomes more feasible with this technology. Thus, the complex connection between consciousness and reality can be understood more clearly. In conclusion, quantum computers can lead to major changes not only in the field of technology, but also in philosophical and scientific thought. This can accelerate the expansion and flexibility of our perception of reality. How does the quantum observer create reality? In quantum mechanics, the observer effect refers to the fact that the state of a particle becomes definite at the moment of observation. In other words, particles exist in a superposition of many possible states until they are measured. But when the observer enters the picture, one of these possibilities becomes reality. This suggests that reality is shaped by the presence of the observer. Whether the observer is conscious or unconscious is debatable. But what is certain is that observation has an effect on quantum systems. This fundamentally alters the classical physics understanding of objects as independent and fixed entities. Reality is now seen as a dynamic process that interacts with the observer. Without an observer, reality is potentially uncertain and fluid. This supports the idea that consciousness is one of the fundamental building blocks of the universe. From a philosophical perspective, this situation deepens the debate between idealism and realism. Is reality an objective entity outside the mind? Or is it a phenomenon created by the mind itself? The quantum observer introduces new dimensions to these questions. It raises the possibility that consciousness is a creative force that shapes reality. Finally, the observer effect could serve as a bridge between science and metaphysics. This understanding shows that consciousness is not merely a passive observer, but an active creator. Thus, the boundaries between reality, consciousness, and matter become blurred, and the universe can be conceived as a living, conscious entity. How does the quantum multiverse theory expand reality? The quantum multiverse theory proposes that for every quantum event, the universe branches out and creates many different realities. In this case, reality is not limited to a single universe, but is seen as a vast multitude consisting of an infinite number of parallel universes. Each universe exists as an independent world where different possibilities come to fruition. This theory radically expands the concept of reality and defines the world we perceive as just a small part of it. Beyond classical determinism, the universe itself is filled with infinite possibilities. This prompts us to rethink the relationship between consciousness and reality. Perhaps consciousness can travel between these multiverses or exist simultaneously in multiple universes. From a philosophical perspective, the theory of multiple universes also reshapes the concepts of free will and destiny. Every choice occurs in a different universe, and we may be traveling through these infinite alternatives. This deepens the meaning of existence and humanity's place in the universe. In conclusion, the quantum multiverse theory eliminates the boundaries of reality and demonstrates that the relationship between consciousness and the universe is much more complex and flexible. This opens up new and exciting horizons in understanding the universe. How does consciousness affect quantum processes? The idea that quantum processes can be shaped by consciousness suggests that consciousness is not a passive observer, but an active creator. Events at the quantum level are determined by the collapse of probabilities, and it is thought that this collapse can be triggered by consciousness. Thus, consciousness becomes a dynamic force that determines the fundamental building blocks of the universe. This approach challenges classical physics and materialism. Consciousness is not merely the result of biochemical processes in the brain, but an active agent in the fundamental workings of the universe. The quantum consciousness connection reveals the direct link between mental experiences and physical reality. Philosophically, this offers a new solution to the age-old debate between consciousness and matter. Consciousness may be the fundamental force that shapes matter, and thus, reality becomes a structure created by consciousness. This supports the view that the universe is alive and conscious. Finally, the influence of consciousness on quantum processes may open the door to scientific explanations of spiritual experiences and psychic phenomena. This shows that consciousness is not limited to the brain and has a universal dimension. How does quantum uncertainty affect the nature of reality? Heisenberg's uncertainty principle states that the position and momentum of a particle cannot be known with certainty at the same time. This fundamental principle shows that reality is not certain, but rather full of possibilities. Classical physics assumes that every moment in the universe is definite and measurable. But quantum uncertainty rejects this. This indicates that the universe is not based on absolute certainty, but on a dynamic and variable structure. The uncertainty principle reveals that it is impossible to limit reality to only observable and measurable phenomena. The nature of the universe possesses a complexity that transcends our perception and measurement methods. This complexity implies that the relationship between consciousness and matter is much deeper than previously thought. This is because our measurement tools cannot fully capture reality. Consciousness plays an active role in this measurement process. Philosophically, uncertainty shows that reality is not a fixed and rigid structure, but rather a network of potential states in constant flux. This supports the idea that existence is not static, but a fluid and ever-evolving process. Consciousness may be a central actor in this process, determining and shaping potentials. In conclusion, quantum uncertainty renders reality more flexible, uncertain, and multi-layered. This highlights the need for a new paradigm in understanding the nature of the universe and consciousness. Reality is a journey through a sea of possibilities rather than certainty. And consciousness is the guide on this journey. How does the quantum nature of time change our perception of reality? Classical physics defines time as a unidirectional, linear, and constant flow. However, quantum theories show that the nature of time is much more complex and uncertain. In quantum processes, time can transcend causality, and some interpretations even argue that time is a fundamental illusion. This perspective implies that time is not independent of the fundamental structure of the universe, but rather plays a role in shaping consciousness and reality. The quantum nature of time leads to a blurring of the sharp distinctions between past, present, and future. Quantum correlations and entanglement show that connections can be established even between different time frames. This suggests that time is not a linear flow, but rather a multidimensional and flexible structure. As a result, our perception of reality undergoes radical changes from a philosophical perspective. The idea that time is not a real flow, but an experience related to consciousness, gains strength. Perhaps time is a phenomenon that emerged with the evolution of consciousness and is a creative element within reality. In this case, the past and future become dimensions that exist within mental structures and perception. In conclusion, the quantum nature of time fundamentally shakes our understanding of reality. Time is not just a clock measured from the outside, but a dynamic structure that interacts with consciousness. This perspective allows for a much deeper, more complex, and more holistic understanding of the universe and consciousness. How do consciousness and quantum interactions shape reality? In quantum physics, the idea that consciousness is not merely a passive observer, but an active element influencing the state of quantum systems is gaining increasing acceptance. This interaction suggests that reality is shaped not only by physical laws, but also by the intentions and perceptions of consciousness. Thus, reality becomes a living, dynamic process rather than a fixed, external entity. Consciousness quantum interactions demonstrate the fundamental connection between consciousness and the universe. This connection implies that there may be a two-way interaction between consciousness and quantum events occurring at the level of matter and energy. In other words, consciousness does not passively observe the physical world, but actively contributes to its formation. This is consistent with many mystical and spiritual teachings. The idea that consciousness creates reality and is in constant interaction with the universe is beginning to be supported by scientific foundations. Thus, reality can be thought of as a reflection and expansion of consciousness. Ultimately, consciousness and quantum interactions are fundamental processes that shape reality. This interaction deepens our perception of reality and reveals that the universe is a living, conscious, and creative whole. Thus, the boundaries between the universe and consciousness dissolve, giving rise to a new understanding. Quantum field theory and the fundamental structure of reality. Quantum field theory reveals that the fundamental particles of the universe are not fixed particles, but excitations of continuously vibrating quantum fields. This approach explains matter and energy as a single whole and shows that information and energy fields lie at the foundation of reality. Thus, reality is a network of energy and information that ripples beyond objects. This theory states that there are fields in constant motion and interaction at every point in the universe. These fields give rise to quantum particles and shape matter. Thus, reality is not a static and rigid structure, but a dynamic, constantly changing, and interacting system. The existence of quantum fields also lays the groundwork for consciousness to merge with the universe. Consciousness can interact with these fields and play a role in the perception and creation of reality. This suggests that consciousness is not merely a phenomenon of the brain, but a universal property. In conclusion, quantum field theory defines reality as networks of information, energy, and interaction. These networks may be the points where consciousness merges with the universe and fundamentally transform our perception of reality. Thus, the universe can be seen as a living, conscious organism. In this context, the constantly vibrating nature of quantum fields undermines the classical physics understanding of a static and mechanical universe. Through the interaction of energy fields, the universe is no longer merely matter. It becomes intertwined with abstract but fundamental elements such as information and consciousness. The dynamic structure of quantum fields indicates that every event in the universe is based on complex energy and information exchanges. This shows that reality is not made up of absolute objects, but rather a whole of constantly forming processes. Thus, the universe functions like a vast network that is alive, breathing, and interacting with consciousness. Furthermore, the interaction between consciousness and quantum fields not only allows us to perceive physical reality, but also grants us the capacity to shape it. This implies that consciousness transcends the role of a passive observer and becomes an active agent. How does quantum entanglement and universal connection fundamentally change our perception of reality? Quantum entanglement is the phenomenon whereby two or more particles become instantly connected to each other. Regardless of how far apart they are, this phenomenon appears as a kind of instant communication or connection that cannot be explained by the laws of classical physics. Entanglement eliminates the meaning of distance between particles and reveals that the universe is based on instantaneous and deep connections that transcend boundaries. This fundamentally shakes our perception of reality because it forces us to see the universe not as a place made up of separate, independent objects, but as a holistic, interconnected, and mutually interactive system. This universal connection is not limited to physical particles. According to some theories, a similar entanglement may exist at the level of consciousness. The idea that consciousnesses are connected to each other through quantum entanglement and form a universal network of consciousness transcends the traditional understanding of individual consciousness. Thus, reality emerges as a complex web woven not only by physical, but also by mental and spiritual connections. These connections represent a dimension of reality that transcends space and time, beyond human perception. From a philosophical perspective, quantum entanglement reinforces the idea of universal wholeness and unity. The interdependence of particles shows that everything in the universe is connected. This opens the door to a perspective where classical distinctions become meaningless and all existence is unified in a single consciousness or entity. This understanding that consciousness and reality are inseparable allows us to comprehend the universe as a whole. Finally, quantum entanglement holds great potential for technological and scientific advances. Developments in quantum communication, quantum cryptography, and quantum computing make practical applications of universal connectivity possible. However, this technology also shows us that we need to rethink the boundaries between reality and consciousness. This is because entanglement requires a fundamental rethinking of the basic structure of the universe and consciousness. Quantum vacuum energy and the reality of space. Quantum vacuum energy shows that the space we consider to be physical space is actually filled with infinite energy. In the classical sense, there is nothing in a vacuum. However, quantum theory reveals that the vacuum is filled with constantly fluctuating energy waves and virtual particles. This indicates the existence of an invisible yet powerful energy ocean at the core of reality. The vacuum is not a passive medium, but an active force field shaping the building blocks of the universe. These energy fluctuations are connected to fundamental phenomena such as the expansion of the universe, dark energy, and even gravity. The mysterious energy of space plays a central role in the formation of matter and energy. Thus, reality transforms into a structure supported by an invisible yet dynamic energy network. Consciousness can interact with this energy field and access the potential powers that exist in the depths of the universe. From a philosophical perspective, quantum vacuum energy redefines the concepts of emptiness and fullness. Emptiness is no longer nothingness, but the source of existence. This perspective blurs the line between existence and non-existence and shows that there is a continuous process of creation at the core of reality. The role of consciousness in this process leads to the perception of the universe as a consciousness that constantly recreates itself. In conclusion, quantum vacuum energy and the reality of space offer a profound understanding of the nature of the universe and consciousness. Space is seen as a silent but powerful creative force in the universe. And when combined with consciousness, it becomes a dynamic element that shapes reality. Quantum consciousness theories and the challenge to classical consciousness. Quantum consciousness theories pose a fundamental challenge to traditional scientific approaches to the nature and functioning of consciousness. The classical understanding of consciousness interacts with fields that exist at the quantum level. It is thought that consciousness operates in accordance with the principles of quantum superposition, entanglement, and uncertainty. This perspective reveals consciousness as a widespread, dynamic, and complex phenomenon in the universe, elevating it from a product of individual brains to a universal layer of reality. Thus, quantum consciousness theories, which transcend the limits of classical consciousness, raise new and radical questions about the nature, origin, and evolution of consciousness. These questions reignite philosophical and scientific debates such as, is consciousness merely a product of brain activity? And how can we understand whether consciousness is a fundamental entity or an emergent property? More importantly, quantum consciousness theories have profound implications for how humans perceive their place in the universe and their perception of reality. While the classical view positions consciousness as a passive observer, quantum consciousness models suggest that consciousness is actively interacting with the fundamental building blocks of the universe. This shows that consciousness is not merely a system that responds to environmental stimuli, but also a creative and transformative force that shapes reality. This active role of consciousness at the quantum level requires us to rethink concepts such as free will, intention, and creativity. It asserts that free will is not merely an illusion, but an effective factor in the formation of reality through its interaction with universal energy fields. This allows human existence and the nature of consciousness to be viewed as a flexible and creative system, rather than a deterministic and mechanical universe where potential energy and information fields are in constant interaction. This challenge posed by quantum consciousness theories triggers a profound transformation in the fields of science, philosophy, and spiritual thought, calling for a rediscovery of humanity's place in the universe by acknowledging consciousness as one of the fundamental elements of reality. In this context, quantum consciousness theories, which push the boundaries of classical consciousness, point not only to a scientific paradigm shift, but also to a revolutionary transformation in the way humanity understands itself and the universe. The dance between consciousness and time in quantum reality. In the context of quantum reality, The relationship between consciousness and time emerges as an extremely complex and profound dance that goes far beyond classical understandings. While time is accepted as a linear, fixed, and objective flow in traditional physics and philosophy, the nature of time in the quantum world is completely different. Time is a flexible, bendable, and multi-layered dimension that interacts with particles and energy fields. Consciousness is not merely an observer of this temporal dimension, but an active participant who experiences, directs, and shapes the flow of time. Quantum consciousness theories argue that consciousness is a universal entity and that time operates directly intertwined with this consciousness. Thus, consciousness and time become two fundamental elements in the universe that are inseparable, mutually influencing and shaping each other. This shared dance demonstrates that time does not progress along a fixed line, but can take on different forms, speeds, and experiences through consciousness's perceptions and intentions. Quantum entanglement and superposition phenomena reveal a reality where consciousness bends the perception of time, blending past, present, and future into layers of existence. This situation forms the theoretical basis for time travel, parallel universes, and multiple timelines, which are considered impossible within the framework of classical physics. The complex relationship between consciousness and time leads us to rethink the structure of the universe and the way existence is experienced. Furthermore, quantum consciousness theories argue that time is not an absolute reality, but rather a flexible and relative phenomenon experienced and created by consciousness. From this perspective, time is not merely a process flowing in the external world, but a reality shaped and constantly rewritten by the creative act of consciousness. By blurring the line between past and future, consciousness makes it possible for momentary experiences, memories, and possibilities for the future to exist simultaneously. At the quantum level, the interaction of consciousness with time creates a unity that encompasses both the continuity and change of the universe. This breaks down the fixed and unidirectional perception of time, making the simultaneous existence of multiple realities and experiences possible. Thus, the relationship between time and consciousness becomes a fundamental key to understanding existence itself. For it is through this relationship that the human mind is not merely a passive witness to the past and future, but also the creative architect of the universe within time. This shared dance between consciousness and time in quantum reality opens new doors to unlocking the universe's deepest secrets and helps us understand the multi-layered, dynamic, and consciousness-intertwined nature of reality. This comprehensive journey into the nature of quantum reality and consciousness offers us an understanding that stands at the intersection of modern science, philosophy, and even spiritual thought. In our quest to make sense of the universe, we went beyond the laws of classical physics and delved into the unknown yet highly meaningful world of quantum mechanics. We saw that time is not a unidirectional and fixed flow, and that space is not a rigid and unchanging ground, but a constantly fluctuating, complex, and flexible structure. It has emerged that consciousness is much more than a passive observer. It is actually deeply connected to the universe at the quantum level and actively interacts with it. The universal connections of quantum entanglement have led us to the idea that we are part of a cosmic consciousness network, detached from individual entities. Reality thus ceases to be an objective, fixed, and external concept, transforming into a complex dance of consciousness, energy, information, and time. The deterministic and mechanical universe predicted by classical physics gives way to a dynamic, open-ended, and conscious living organism. As quantum field theories suggest, Matter and energy exist not as fixed particles, but as constantly vibrating fields. Within these vibrations, consciousness merges with universal energy to shape reality. This profound understanding is not only a scientific revolution, it also requires fundamental changes in the philosophical and spiritual dimensions of existence. New definitions of time, space, and consciousness take us from being part of the universe to the idea that we are the universe itself. Individual selves within the universal consciousness network are actually different manifestations of the whole. Reality is the field of interaction between these manifestations. Thus, the meaning of life, existence, and experience is not limited to the physical universe outside us, but is deepened and expanded by the experience of inner consciousness. Quantum consciousness theories go beyond the mind-body problem and reveal that consciousness is a fundamental property of the universe and points to a form of existence far beyond the limits of classical neurology. Consciousness is not seen as a local phenomenon occurring in the brain, but as a universal process and creative force at the quantum level. This opens new doors to fundamental human questions such as free will, creative potential, and the meaning of existence. In conclusion, the quantum reality paradigm is reshaping our understanding of the universe and the experience of consciousness, inviting us on a bold journey toward new discoveries, deeper insights, and perhaps the ultimate quest for truth at the boundaries of existence. At this point, where science, philosophy, and spiritual thought intertwine, reality is becoming a dynamic whole that is constantly created and reshaped by our perceptions, intentions, and conscious experiences. Thus, our quest to unlock the secrets of the universe becomes a journey to explore the limits of our own consciousness, a journey that reveals the most fundamental and fascinating mystery of what it means to be human. In this complex and fascinating reality, the flow of time is not merely an external process, but a stage where consciousness is constantly evolving. Space is not a solid ground, but a living network where consciousness and energy dance. And consciousness is not merely an experiencer, but an active creative force that actively shapes reality. This is precisely why quantum reality opens a brand new door for us to understand the infinite, mysterious, and interconnected nature of the universe and ourselves. When we step through this door, we encounter a completely new universe, where our concept of reality is fundamentally transformed, where consciousness is integrated, and where time and space extend beyond our ordinary perceptions. This universe is a realm of profound wisdom, creativity, and interconnectedness, and we are both the explorers and the creators of this realm. As we seek to understand the relationship between quantum reality and consciousness, we embark on a journey of discovery that challenges the limits of humanity's answers to the most fundamental questions of existence. For this discovery is not merely about the external structure of the universe, but a revolution that fundamentally transforms our internal experiences, perceptions, and how we define ourselves. The concepts of uncertainty, probability, and entanglement introduced by quantum mechanics prevent us from seeing reality as merely a collection of physical objects and mechanical laws. Instead, they compel us to understand the universe as a constantly evolving, dynamic, and multi-layered system in which consciousness, quantum entanglement, and superposition are intertwined. Thus, we are not merely small parts of the universe. We are a constantly creative force that experiences the universe itself through consciousness. This consciousness actively shapes reality and reveals its potential as it interacts with the universe at the quantum level. Therefore, reality is not fixed and objective, but a living and changing network created by our subjective experiences intentions, and perceptions. This requires us to rethink the meaning of our existence, free will, and the nature of conscious experience. Quantum consciousness theories, which argue that consciousness is not merely a product of the brain, but one of the fundamental building blocks of the universe, blur the boundary between humans and the universe. They transform us into a network of consciousness that is in harmony with the universe, connected to it and integrated with it. Therefore, the quantum reality paradigm transcends being merely a scientific theory. It becomes a consciousness revolution that fundamentally transforms humanity's understanding of itself, the universe, and reality. Emerging at the intersection of science, philosophy, and spiritual thought. This new paradigm invites us to constantly ask deeper questions and boldly approach the mysteries of the universe in order to discover the multi-layered nature of reality and its structure intertwined with consciousness. It is precisely at this point that our quest for the mysterious nature of existence transforms into a quest for transcendent meaning, wholeness, and inner wisdom. We recreate and give meaning to reality as creative and exploratory consciousnesses that carry the universe within us rather than being lost in it. Reality is stranger than we imagine, and science is the most powerful tool we have to understand that strangeness. $13.8 billion years ago, everything we know exploded into existence from a point smaller than an atom. This has been our story, our cosmic genesis, the bedrock of our understanding. But the James Webb Space Telescope, an instrument of impossible precision, a $10 billion eye designed to gaze upon the universe's infancy, has just found galaxies that were already ancient when the universe was supposedly still a baby. We are seeing stars that formed heavy elements before the cosmos had time to cook them, massive black holes that grew impossibly fast, and structures so perfectly organized they shouldn't exist in a chaotic, young universe. The most powerful telescope ever built wasn't meant to destroy our origin story, but that's exactly what it's doing. Prepare yourselves. We begin. The James Webb Space Telescope cost $10 billion and took 30 years to build. This monumental effort, a testament to human curiosity and engineering, was not just about getting better space photos. Scientists had a specific, profound mission to prove that our story of cosmic creation was absolutely correct. For decades, we have told ourselves a simple, elegant tale. The Big Bang happened 13.8 billion years ago. Then came 400 million years of cosmic darkness, a silent, starless epoch while the universe cooled and gravity slowly, patiently, began to gather the primordial gas. Those first stars, when they finally ignited, were supposed to be simple, monstrously large, and made only of hydrogen and helium, the raw ingredients forged in the initial fireball. Galaxies, in this narrative, should have grown gradually, messily, over billions of years through countless collisions and mergers, like cities built slowly from scattered villages. This timeline was not just a theory. It was the foundation of modern cosmology. Every textbook, every documentary, every elegant equation that described our universe relied on this sequence of events. The standard model of cosmology, a framework of stunning predictive power, was built upon this assumption of a slow, hierarchical formation of structure. The James Webb Telescope was designed to be the ultimate witness to this process. Its unparalleled infrared vision could peer back through the expanding darkness, through the veil of cosmic dust, to the very edge of the cosmic dawn. It was meant to show us those first primitive stars struggling to ignite, to capture the faint, red-shifted light of the first fledgling galaxies as they flickered into existence. We expected to see a chaotic, violent universe slowly, painstakingly, organizing itself into the cosmos we know today. The telescope's 18 hexagonal mirrors, coated in a whisper-thin layer of gold, were polished to a perfection measured in atoms. Its instruments were calibrated to detect the faintest whispers of ancient light, photons that had traveled for more than 13 billion years to reach us. Scientists prepared to celebrate as the first observations confirmed what their powerful computer simulations had predicted for decades. The early universe should look young, disorganized, and exactly as messy as you would expect from a cosmos just learning how to exist. But when James Webb opened its golden eye and looked back toward the beginning of time, it did not find confirmation. It did not find the expected chaos. It did not find the primitive, stumbling galaxies of our theories. Instead, it discovered something that made astronomers question everything they thought they knew about cosmic history. The discoveries staring back at us from the cosmic dawn challenged not just the details of how galaxies formed, but the entire timeline of cosmic evolution. The implications reach far beyond astronomy. If our most fundamental story about reality is wrong, what does that mean for physics, philosophy, and our place in the universe? The telescope that was meant to prove our origin story might instead destroy it completely. 400 million years after the Big Bang, the universe should have been a cosmic wasteland. To put that into perspective, if the entire history of the cosmos was compressed into a single calendar year, we are looking at January 2nd. At that point, galaxies should be tiny, primitive collections of the very first stars, little more than glowing smudges in the endless dark. What James Webb found instead were massive, mature galaxies that looked as if they had been around for billions of years. These are not small collections of newborn stars struggling to survive. We are seeing galaxies with masses equivalent to 100 billion suns, perfectly organized into spiral arms and central bulges. Our own Milky Way galaxy took over 13 billion years to reach this level of development. Yet here are galaxies that somehow achieved this complexity when the universe was barely out of diapers. The numbers simply do not add up. Our most sophisticated computer simulations, which have successfully modeled the evolution of the universe for decades, show that galaxies this massive should take at least 2 billion years to form, through the slow, arduous process of smaller galaxies merging together. But we are seeing them when the universe was only 400 million years old. It is like finding a fully grown oak tree in a garden that was planted yesterday. Dr. Ivo Labbé from Swinburne University described these discoveries as galaxy monsters that shouldn't exist. His team found galaxies so massive, they make up almost as much matter as all the stars that should exist in the entire observable universe at that time. The math simply does not work with our current understanding of cosmic evolution. It is a statistical impossibility, a cosmic contradiction written in the light of ancient stars. Even more puzzling is how organized these galaxies appear. The Big Bang theory predicts that early galaxies should be chaotic and irregular, slowly forming structure through gravitational interactions over cosmic time. Instead, James Webb is showing us galaxies with clear spiral patterns, well-defined central bulges, and organized star formation regions. These are features that should take billions of years of quiet, stable evolution to develop. This discovery is forcing astronomers to confront an uncomfortable possibility. Either our understanding of how fast galaxies can form is completely wrong, or our timeline of cosmic history needs a major revision. Some scientists are beginning to whisper about alternative theories that could explain these observations. Theories that were once dismissed as fringe ideas. But accepting those alternatives means abandoning much of what we thought we knew about the universe. The implications stretch beyond just galaxy formation. If massive, organized galaxies existed this early, they would have profoundly influenced the entire structure of cosmic evolution. The gravitational effects of these monster galaxies should have left traces throughout the universe that we simply do not see in other observations. Yet, the evidence keeps mounting that these impossible galaxies are absolutely real. In the beginning, the universe knew only three elements: hydrogen, helium, and tiny, almost negligible traces of lithium. Every other element in the periodic table, the building blocks of planets, of life, of you, had to be forged inside the nuclear furnaces of stars and scattered through space when those stars died. This process of cosmic alchemy takes time, billions of years of it. Yet, James Webb is finding heavy elements in galaxies that formed when the cosmos was still a cosmic infant, a time when such complexity should have been impossible. Picture a star as a cosmic kitchen. It starts with the simplest ingredients, hydrogen and helium, and slowly cooks them into heavier elements through the intense pressure and heat of nuclear fusion. Carbon, oxygen, silicon, iron, all these elements require multiple generations of stars to create and distribute. The very first stars, the primordial giants, had to live their entire, brilliant, violent lives, explode as supernovae, and seed the surrounding space with these newly forged heavy elements. Only then could the next generation of stars form, incorporating those elements into their own structure and into the planets that would orbit them. This stellar cooking process is like a cosmic assembly line that cannot be rushed. The most massive stars burn through their fuel quickly and explode within a few million years. But even this fastest of cosmic assembly lines needs hundreds of millions of years to produce significant amounts of heavy elements. The universe at 400 million years old simply had not had enough time for this process to work. Yet, spectroscopic analysis of these early galaxies, a technique that breaks light down into its constituent colors to reveal its chemical composition, shows clear signatures of oxygen, carbon, and even heavier elements like silicon and magnesium. The concentrations are not trace amounts that might be explained by a few unusually fast-burning stars. We are seeing metal abundances that suggest multiple generations of star formation and death had already occurred. A level of chemical enrichment that rivals much younger, more evolved systems. Dr. Emma Curtis Lake, who led some of these early spectroscopic observations, described finding galaxies with metallicities that were simply staggering. The spectral lines, the dark bands in the rainbow of starlight that correspond to specific elements, do not lie. These galaxies contain elements that should not exist in such quantities for billions more years of cosmic evolution. This discovery creates a cascade of problems for our cosmic timeline. If heavy elements existed this early, then planet formation could have begun much sooner than predicted. Rocky planets like Earth, which require these heavier elements to form, could have been a common feature of the very early universe. The implications for when and where life might have first appeared in the universe become staggering. Suddenly, the timeline for biology is pushed back billions of years into an era we once thought was barren and inhospitable. Some astronomers are proposing that the very first stars, the population 3 stars, might have been much more massive than we thought, burning through their lives and creating heavy elements at unprecedented rates. Others suggest that star formation itself might work differently in the early universe than it does today, with different efficiencies and different outcomes. But both of these explanations require us to revise fundamental assumptions about stellar physics. Assumptions that have been tested and confirmed for decades. The elements James Webb found should not exist yet, but they are there, written in the light of ancient galaxies, challenging everything we thought we knew about cosmic chemistry. What we discovered next makes the heavy element problem look simple by comparison. Imagine trying to build a skyscraper during an earthquake while blindfolded. That is what galaxy formation should have looked like in the early universe. The cosmos was violent, chaotic, and filled with dark matter and gas crashing together in random collisions. Galaxies should have grown slowly and messily through countless mergers over billions of years. What James Webb found instead were galaxies that looked as if they had been designed by a cosmic architect. The Hubble Space Telescope had already shown us that distant galaxies appear more irregular and chaotic than nearby ones. This made perfect sense. We were looking back in time to see galaxies in their awkward teenage years, still growing and organizing themselves. James Webb was supposed to push even further back, to see cosmic toddlers stumbling around in the dark. Instead, we found galaxies with clear spiral arms, organized central bulges, and structured star formation patterns. These features require delicate gravitational balance and billions of years of quiet, stable evolution to develop. In our own cosmic neighborhood, only the most mature, undisturbed galaxies display such perfect organization. Yet here they were, in the cosmic dawn, looking impossibly sophisticated. Dr. Stephen Finkelstein from the University of Texas described these discoveries as finding adult galaxies in a cosmic nursery. The level of organization defies everything we know about hierarchical structure formation. The theory that predicts small objects merge to form larger ones over cosmic time. These galaxies appear to have skipped their messy childhood entirely, emerging fully formed from the chaos of the early universe. The smooth, thin disk structures are particularly puzzling. In today's universe, galaxy disks form through a complex process where gas slowly settles into stable, rotating patterns over hundreds of millions of years. Early in cosmic history, frequent mergers and chaotic gravitational conditions should prevent such delicate structures from forming or surviving. Yet, James Webb is showing us pristine spiral patterns that look as if they have never been disturbed, as if they have been spinning peacefully for eons. Even more mysterious are the central supermassive black holes that seem to be perfectly coordinated with their surrounding galaxies. In the modern universe, we observe tight correlations between the mass of a galaxy's central black hole and the properties of its host galaxy. This relationship takes billions of years to establish through a complex dance of feedback between star formation and black hole growth. Finding such coordination in young galaxies suggests processes we do not understand, a form of coevolution that happens almost instantaneously. The implications of this discovery challenge the entire concept of cosmic evolution. If galaxies can organize themselves this quickly, then our understanding of how structure forms in the universe needs a complete overhaul. It suggests that there is a hidden organizing principle at work, a force or a mechanism that we have not accounted for in our models. The smooth, organized galaxies James Webb discovered should not exist for billions more years, but their perfect spiral arms are just spinning us toward an even stranger discovery, about rotation speeds that appear to break the laws of physics. Galaxies rotate like cosmic hurricanes, vast, swirling systems of stars, gas, and dust held together by the gravitational embrace of dark matter halos that surround them like invisible cocoons. The faster a galaxy spins, the more mass it needs to prevent itself from flying apart. This fundamental relationship between rotation speed and mass is one of the most reliable and well-tested rules in astronomy. But James Webb found ancient galaxies spinning so fast they should have torn themselves to pieces billions of years ago. When astronomers measure how fast stars move in the disks of distant galaxies, they can calculate exactly how much total mass the galaxy contains. It is a simple application of physics, like watching cars on a circular racetrack. The faster they go without flying off the track, the steeper the banking of the road must be. In galaxies, that banking is provided by gravitational mass, mostly in the form of dark matter. The problem is that these early galaxies are rotating at speeds that require dark matter halos much more massive than anything our computer simulations of structure formation can produce. Some of these ancient galaxies are spinning at 300 kilometers per second, when they should be limited to perhaps 150. That is like finding a motorcycle taking a tight turn at twice the speed that should send it skidding into the wall. Dr. Claude-André Fauché-Giguère from Northwestern University has been studying these rotation curves and describes them as impossible under current models of galaxy formation. The dark matter halos required to stabilize such rapid rotation would be so massive that they should dominate the entire region of space around them. Yet, we do not see evidence for such monster halos in the structure of the cosmic web. Even stranger is how quickly these rapid rotation patterns must have established themselves. In today's universe, galaxy disks build up their rotation gradually as gas settles into stable orbits over hundreds of millions of years. But these ancient galaxies appear to have reached their maximum spin almost immediately after forming. It is like finding a figure skater already in a perfect, high-speed pirouette the moment they step onto the ice. The physics becomes even more problematic when you consider the conservation of angular momentum. As galaxies form from collapsing clouds of gas, they should spin up gradually as they shrink, just like a figure skater pulling in their arms. But the rotation speeds James Webb measured suggest these galaxies started with far more angular momentum than the cosmic web should have been able to provide. The initial conditions of the universe simply did not contain enough rotational energy to explain these observations. Some theorists are proposing exotic solutions, involving modified theories of gravity or alternative dark matter models that could provide the extra gravitational pull needed. Others suggest that early galaxy formation might involve processes we have never considered, like the transfer of angular momentum through cosmic magnetic fields. But every explanation requires abandoning well-tested physics or accepting that the early universe operated under a completely different set of rules. These impossibly fast-spinning galaxies are rotating us toward an even more disturbing discovery about collisions that happened before galaxies should have even had time to meet. Galaxy mergers are cosmic train wrecks that unfold over hundreds of millions of years. When two galaxies collide, their gravitational dance creates tidal tails, stellar streams, and distorted structures that astronomers can recognize like forensic evidence at a crime scene. James Webb found this evidence in galaxies that formed when the universe was so young that such collisions should not have been possible yet. The timeline problem here is severe. According to our models, the first galaxies were tiny, isolated islands of stars scattered across vast distances of empty space. They were like cosmic hermits, too far apart and too small to interact with each other in any significant way. Major galaxy mergers, the kind that dramatically reshape galaxies, should have waited until the universe was at least 1 billion years old, when cosmic structures had grown large enough and close enough to gravitationally influence each other. Yet, James Webb is showing us clear merger signatures in galaxies from just 400 million years after the Big Bang. We are seeing tidal streams of stars being pulled away from galactic cores, double nuclei that indicate recent collisions, and asymmetric, distorted structures that can only result from gravitational encounters between massive objects. Dr. Jehan Kartaltepe from the Rochester Institute of Technology has been analyzing these early merger signatures and describes them as finding car crashes in a world where cars have not been invented yet. The morphological features are unmistakable. These galaxies have definitely collided with other massive systems, but the cosmic timeline says such collisions should be impossible this early in universal history. The discovery gets even more puzzling when you consider the merger rates. In the local universe, major galaxy mergers are relatively rare events. A galaxy like the Milky Way might experience one significant merger every few billion years. But in these early observations, merger signatures appear in almost every massive galaxy James Webb examines. It is as if the young universe was experiencing a collision epidemic, a period of frantic, chaotic merging that our theories never predicted. Even more problematic is the scale of these ancient mergers. We are not seeing small galaxies absorbing tiny companions. These are major mergers between systems that are already massive and well-developed. The energy required to disrupt such large galaxies and then reorganize them into the structures we observe should take billions of years. Yet, we are seeing the aftermath when the universe was barely 500 million years old. The implications of this discovery cascade through our understanding of cosmic evolution. If major mergers were common this early, they would have triggered massive bursts of star formation and fed the central black holes at unprecedented rates. This should have left observable signatures throughout the universe, in the distribution of matter and the properties of the cosmic background radiation that we simply do not see. Some astronomers are beginning to question whether our fundamental timeline of structure formation is completely wrong. Maybe the universe organized itself much faster, much more violently, and much more efficiently than we ever imagined possible. But the evidence for impossible timing does not stop with galaxy collisions. Next, we discovered something even more fundamentally challenging about the cosmic microwave background itself. The cosmic microwave background, or CMB, is the universe's baby picture. It is a snapshot of what the cosmos looked like just 380,000 years after the Big Bang. A faint, ancient light that carries the imprint of the tiny density fluctuations that would eventually grow into galaxies, stars, and everything we see today. But James Webb's observations suggest that this baby picture might be telling us the wrong story about how the universe actually developed. The CMB shows us a universe that was remarkably smooth and uniform in its early days. The variations in density were incredibly small, just 1 part in 100,000. These tiny ripples in the cosmic fabric were the seeds that would slowly, over billions of years, grow through gravitational attraction into the vast, large-scale structures we observe today. Cosmologists have used sophisticated computer simulations to grow these seeds forward in time, predicting exactly what the universe should look like at any given epoch. These models are incredibly detailed, tracking how dark matter clumps together, how gas flows between galaxies, and how stars form within those galaxies. These simulations confidently predict that at the time James Webb is observing, galaxies should be small, irregular, and relatively rare. But that is not what we are seeing. The massive, organized galaxies that James Webb discovered require initial density fluctuations that were much larger than what the cosmic microwave background recorded. It is like finding full-grown trees in a field where the soil analysis says only grass seeds were planted. The numbers do not match. Dr. Rajendra Gupta from the University of Ottawa has been comparing James Webb observations with CMB predictions and describes the mismatch as fundamentally problematic. The early universe appears to have had far more structure-forming power than the baby picture suggests was possible. The discrepancy is not subtle. Some of the galaxies James Webb found are so massive that they require regions of space that were overdense by factors that the CMB says should not exist. The statistical probability of such massive galaxies forming from the observed initial conditions is essentially zero. We should not be seeing them, and yet we are. This creates a paradox that strikes at the heart of modern cosmology. Either our interpretation of the cosmic microwave background is wrong, or our understanding of how cosmic structures grow from initial fluctuations needs a complete revision. Both possibilities would require abandoning fundamental assumptions that have guided cosmology for half a century. Some theorists are exploring exotic solutions, involving things like primordial black holes that could have acted as seeds for early galaxy formation, or modified theories of gravity that could have accelerated the growth of structure. Others are beginning to suggest that the CMB might not be the pristine, untouched record of initial conditions we once thought it was. Perhaps later events in the universe's history have altered its properties in ways we do not yet understand. The mismatch between our cosmic baby picture and what James Webb actually found growing in the universe is pushing us toward an even more disturbing discovery about black holes that grew impossibly fast. Quasars are the universe's most powerful lighthouses. Brilliant, Distant objects powered by supermassive black holes that consume matter at extraordinary rates and blast energy across billions of light years. These cosmic monsters contain millions, or even billions, of times the mass of our Sun. But James Webb found fully grown quasars shining when the universe was so young that black holes should have barely begun their journey towards such enormous sizes. Building a supermassive black hole is like constructing a skyscraper, one grain of sand at a time. The process requires patience and a tremendous amount of raw material, even under the most ideal conditions. Black holes can only grow so fast because the very energy they release while feeding heats up and pushes away the matter they are trying to consume. This natural speed limit is a fundamental part of black hole physics. The physics is unforgiving. When matter falls into a black hole, it heats up and glows brightly in an accretion disk before disappearing forever. This intense radiation exerts an outward pressure, acting like a cosmic traffic cop that regulates how much material can approach the black hole at any given time. The maximum growth rate, known as the Eddington limit, means that even a black hole that starts with the mass of 1,000 suns would need over 1 billion years to reach the billion solar mass range. Yet, James Webb discovered quasars powered by billion solar mass black holes when the universe was only 600 million years old. These are not modest black holes still growing toward maturity. They are fully developed supermassive objects, already dominating their galactic environments and powering some of the brightest objects in the cosmos. Dr. Xiaohui Fan from the University of Arizona has been studying these early quasars and describes them as finding adult elephants in a nursery full of mice. The growth rates required to explain these observations exceed the theoretical limits by factors of 10 or more. Either our understanding of black hole physics is incomplete, or these black holes started out much larger than anything our models predict. The discovery becomes even more puzzling when you consider where these black holes came from originally. The very first black holes should have formed from the collapse of the first generation of stars, which themselves took tens of millions of years to form and evolve. This means the seed black holes that would eventually become supermassive should have started with masses equivalent to perhaps 100 suns at most. Getting from 100 solar masses to 1 billion solar masses in 600 million years, while respecting the Eddington limit, is mathematically impossible. It is like trying to drive from New York to Los Angeles in 1 hour while obeying the speed limit. Some theorists are proposing that the first black holes might have formed through completely different mechanisms, like the direct collapse of massive gas clouds, which could have created seed black holes with much larger initial masses. Others suggest that black hole growth in the early universe might not obey the same physical limits we observe today, perhaps through mergers or super Eddington accretion. But these impossibly massive black holes are not just growing. They are feeding star formation at rates that defy our understanding. Stars are born in cosmic nurseries called molecular clouds, where gravity slowly compresses gas and dust until nuclear fusion ignites. This process has natural speed limits built into the physics of how matter behaves under extreme conditions. But James Webb found galaxies forming stars at rates so fast they violate every theoretical maximum we have calculated for stellar birth. In today's universe, even the most active star-forming galaxies, known as starburst galaxies, convert only about 1% of their available gas into stars every million years. This efficiency limit exists because star formation is a messy, wasteful process. When massive stars form, they blow powerful stellar winds and eventually explode as supernovae, heating up and dispersing the surrounding gas. This stellar feedback acts like a cosmic thermostat, regulating how quickly new stars can form. The most extreme star-forming galaxies we observe today create about 1,000 new stars per year. This rate is already considered extraordinary and unsustainable. Galaxies forming stars. This quickly will exhaust their gas supplies within a few 100 million years. Yet, James Webb discovered early galaxies with star formation rates exceeding 10,000 stars per year, sustained over periods that should have been impossible. Dr. Pascal Oesch from the University of Geneva has been analyzing these stellar birth rates and describes them as finding cosmic factories running at 10 times their maximum rated capacity. The energy output from such intense star formation should heat up and expel all the remaining gas, shutting down further stellar birth almost immediately. Yet, these galaxies appear to maintain these extreme star formation rates for hundreds of millions of years. The physics becomes even more problematic when you consider the raw materials required. Forming 10,000 stars per year requires consuming gas at rates that would exhaust even the largest known reservoirs within a cosmic blink of an eye. These galaxies would need a constant resupply of fresh material from their surroundings. But the early universe was much less dense than today, making such massive gas flows unlikely. Even more puzzling is how these galaxies managed to retain their star-forming gas in the first place. The intense radiation from such rapid star formation should create powerful galactic winds that blow gas out of the galaxy entirely. We observe this process in local starbursts, where stellar feedback eventually quenches star formation. But these early galaxies seem to be immune to their own stellar violence, continuing to form stars at a furious pace. The discovery suggests that star formation in the early universe operated under a completely different set of rules than what we observe today. Maybe the primordial gas was denser and colder, allowing it to collapse more efficiently. Maybe the stellar feedback was less effective, or the entire process of stellar birth was fundamentally different when the cosmos was young. Some astronomers are proposing exotic mechanisms involving primordial gas with unusual properties or gravitational conditions that no longer exist in the modern universe. Others suggest that our understanding of stellar feedback and gas dynamics needs a major revision. But these impossible star formation rates are not happening in isolation. They are organizing themselves into structures that challenge our understanding of cosmic evolution itself. The early universe should have been a scene of cosmic chaos, a violent, turbulent place where matter crashed together randomly as gravity struggled to organize the aftermath of the Big Bang. Large-scale structure, the vast network of galaxies and voids that defines the modern cosmos, should have emerged slowly and messily over billions of years through countless random collisions and mergers. But James Webb found a level of cosmic organization that suggests the universe knew exactly what it was doing from the very beginning. Picture the cosmic web as a three-dimensional spider web stretching across billions of light years, with galaxies strung along filaments of dark matter like dewdrops on silk strands. This web structure is one of the most beautiful and organized features of the modern universe. Computer simulations show that it should take at least 1 billion years for such organized patterns to emerge from the smooth, uniform initial conditions after the Big Bang. Yet, James Webb is revealing hints of large-scale structure and organized galaxy distributions in the cosmic dawn. When the universe was only a few 100 million years old, we are seeing aligned galaxy clusters, coordinated star formation patterns across vast distances, and gravitational influences between objects that should still be isolated islands in space. Dr. Casey Papovich from Texas A&M University has been mapping these early large-scale structures and describes them as finding a completed jigsaw puzzle when you expected to see scattered pieces still looking for their places. The level of gravitational coordination between distant objects requires a cosmic web that developed far faster than our models predict. The organization appears at multiple scales simultaneously. Not only are individual galaxies more structured than we expected, but they are also organized into groups and clusters that should not have had time to form. The gravitational binding energy required to hold such systems together suggests they assembled much more quickly and efficiently than the theory of hierarchical structure formation allows. Even more mysterious is how these organized structures maintain their coherence across such vast distances. In the early universe, light had not had enough time to travel between widely separated regions, meaning they could not coordinate their behavior through any known physical mechanism. This is known as the horizon problem. Yet, we are seeing correlated properties, like star formation rates and galaxy orientations, across scales that should be causally disconnected. This cosmic organization problem strikes at the fundamental assumptions about how the universe evolved from smooth initial conditions to the structured cosmos we observe today. If large-scale structure formed this quickly, it suggests either that the initial conditions were not as smooth as we thought, or that there were processes at work that we do not understand. Some cosmologists are exploring ideas about cosmic phase transitions, primordial magnetic fields, or exotic forms of dark energy that could accelerate structure formation. Others are questioning whether the initial conditions after the Big Bang were as smooth and random as we have assumed. But this organized cosmic architecture is not just empty space. It is supporting planetary systems that seem to have formed impossibly early in cosmic history. Rocky planets like Earth require a cosmic recipe that takes billions of years to prepare. You need multiple generations of stars to forge heavy elements, supernova explosions to scatter those elements through space, and then the slow, patient process of gravitational accretion to gather dust and debris into solid worlds. But James Webb has found evidence of planetary systems in galaxies so young that the ingredients for rocky planets should not even exist yet. Planet formation is like cosmic cooking that cannot be rushed. The first stars contained only hydrogen and helium, the simplest elements forged in the Big Bang itself. Every heavier element, the carbon in our bodies, the oxygen we breathe, the silicon in Earth's rocks, the iron in our blood had to be manufactured inside the cores of stars and distributed by their explosive deaths. This process of element production takes time, even after heavy elements become available. Building planets is a slow process. Tiny dust grains must stick together to form pebbles. Pebbles must clump into boulders. Boulders must accumulate into asteroids. And asteroids must collide to build planets over tens of millions of years. The entire sequence, from the death of the first stars to the formation of the first rocky planets, typically requires at least 1 billion years of cosmic evolution. Yet, spectroscopic analysis of some early galaxies shows absorption features that could indicate the presence of dust and, potentially, even planetary debris in systems that formed when the universe was less than 800 million years old. Dr. Kevin Heng from the University of Bern describes these observations as finding evidence of planetary construction in a cosmic era when the building materials should not even exist. The implications of this discovery cascade through our understanding of when and where life might have first appeared in the universe. If rocky planets could form this early, then the conditions necessary for biology might have existed billions of years sooner than we ever imagined. The universe could have been teeming with potentially habitable worlds when our own solar system was still just a distant dream, an unformed cloud of gas and dust. Even more intriguing are the hints of atmospheric absorption in some of these early systems. While we cannot yet definitively confirm the presence of planetary atmospheres in such distant and ancient objects, the spectral signatures suggest the existence of complex chemistry involving heavy elements, arranged in ways that look suspiciously like atmospheric processes. The discovery forces us to reconsider how quickly planetary systems can assemble and begin operating as complex chemical laboratories. Maybe the process of dust grain sticking was more efficient in the early universe, or gravitational processes worked faster in the denser environment of cosmic youth. Some astronomers are proposing that the first planetary systems might have formed through mechanisms we do not observe in the modern universe, perhaps involving primordial materials or gravitational conditions that no longer exist today. But these rapidly forming planetary systems are not just an isolated puzzle. They are challenging our understanding of the cosmic inflation theory itself. Cosmic inflation theory proposes that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang, stretching space faster than the speed of light and smoothing out any initial irregularities. This inflation should have created a universe with very specific, predictable properties, smooth on large scales, with tiny, precisely characterized fluctuations that would slowly grow into cosmic structure over billions of years. But James Webb's discoveries suggest the universe might not have followed the inflationary script at all. Inflation theory makes testable predictions about what the early universe should look like. The density fluctuations that eventually became galaxies should have specific statistical properties, following patterns that reflect the quantum mechanical processes that created them during the inflationary epoch. These fluctuations should be small, nearly scale invariant, and distributed according to precise mathematical relationships. The problem is that the massive, organized structures that James Webb discovered require initial fluctuations that were much larger and more organized than inflation predicts. The theory suggests that regions of space dense enough to form the observed massive galaxies should be extraordinarily rare, so rare that we should not see any in the cosmic volumes that James Webb can observe. Dr. Paul Steinhardt from Princeton University, one of the original architects of inflation theory, who later became one of its most prominent critics, describes these observations as potentially fatal problems for the inflationary paradigm. The statistical properties of the early galaxies do not match what inflation theory predicts should emerge from quantum fluctuations during a period of exponential expansion. Even more problematic is the coherent organization of structure across vast scales. Inflation theory predicts that different regions of space should have evolved independently after the rapid expansion separated them beyond any possible causal connection. Yet, James Webb's observations hint at coordinated properties and structures across distances that should be completely independent, according to inflationary cosmology. This discovery forces cosmologists to confront uncomfortable questions about whether cosmic inflation actually occurred, or whether it worked differently than our models suggest. Alternative theories that never required inflation are gaining renewed attention as potential explanations for James Webb's observations. Some theorists are exploring bouncing universe models, where our cosmos emerged from the collapse and rebound of a previous universe, potentially preserving organizational information that inflation would have erased. Others are investigating modified gravity theories or exotic forms of dark energy that could create the observed structure without requiring an inflationary expansion. The implications of this reach far beyond cosmology and into the realm of fundamental physics. Inflation theory has been intimately connected with our theories of quantum gravity and the earliest moments of cosmic history. If inflation is wrong, it suggests that our understanding of physics at the most fundamental level needs a major revision. But as multiple independent observations point to the same problems, the evidence becomes impossible to ignore. Science advances through the accumulation of evidence, and isolated anomalies can often be explained away by measurement errors, statistical flukes, or an incomplete understanding of the data. But when multiple, independent observations, using different techniques, all point to the same fundamental problem, the scientific community must confront the possibility that the accepted theories are simply wrong. James Webb's discoveries represent exactly this kind of converging evidence crisis. The telescope did not find just one type of anomaly. It discovered massive galaxies where small ones should exist, heavy elements that formed too quickly, organized structures that should be chaotic, rotation speeds that violate physics, collision signatures that predate possible interactions, star formation rates that break theoretical limits, and planetary systems that assembled impossibly fast. Each of these discoveries, taken alone, might be dismissed as an outlier or a statistical fluke, but together, they paint a consistent and deeply troubling picture of a universe that does not follow our rules. Independent research teams, using different analysis methods and looking at different regions of the sky, have confirmed these findings repeatedly. Dr. Labe's galaxy mass measurements have been verified by multiple groups using completely different techniques. The spectroscopic evidence for early heavy elements has been detected in several independent surveys. The impossible rotation speeds have been confirmed through both direct velocity measurements and gravitational lensing studies. Even more compelling is how these diverse anomalies all point in the same direction, toward a universe that organized itself much faster and more efficiently than the standard Big Bang theory predicts. The problems are not random, scattered inconsistencies that might be explained by minor theoretical adjustments. They form a coherent and systematic pattern, suggesting that our fundamental timeline of cosmic evolution is wrong. The statistical weight of this accumulated evidence is becoming overwhelming. When astronomers calculate the probability that all of these observations could be explained by a combination of measurement errors or rare statistical fluctuations, the numbers become vanishingly small. We are not looking at a series of unlucky coincidences. We are seeing systematic discrepancies that demand a profound explanation. This convergence of evidence is forcing theoretical physicists to abandon incremental modifications to existing theories and begin to consider revolutionary alternatives. Dr. Subir Sarkar from Oxford University describes the situation as a paradigm crisis, a term used in the philosophy of science to describe a moment when accumulated anomalies can no longer be accommodated within the existing theoretical framework. The process mirrors historical scientific revolutions, where multiple, independent observations eventually forced a complete theoretical overhaul, just as the discovery of stellar parallax, galactic redshifts, and the cosmic microwave background converged to establish the Big Bang theory in the first place. James Webb's discoveries might be converging to overthrow it. Scientific institutions are beginning to acknowledge that these discrepancies require serious theoretical attention rather than ad hoc explanations. Major funding agencies are directing resources toward alternative cosmological models that could explain James Webb's observations without violating fundamental physics. The accumulated weight of evidence is pushing theoretical physicists toward completely new models of cosmic evolution. Behind closed doors in physics departments around the world, theorists are working frantically to develop alternative cosmological models that could explain James Webb's impossible observations without breaking the known laws of physics. These are not minor adjustments to existing theories. They are revolutionary new frameworks that could replace the Big Bang theory entirely. The quiet urgency of this theoretical work reflects how seriously physicists are taking the mounting evidence crisis. Dr. Neil Turok from the Perimeter Institute has been developing cyclic cosmology models, where the universe undergoes infinite cycles of expansion and contraction, with each cycle preserving organizational information that could explain the rapid structure formation James Webb observed. These models suggest our universe might not have had a beginning at all, but rather emerged from the organized collapse of a previous cosmic cycle. Meanwhile, Dr. João Magejo from Imperial College London is exploring variable speed of light cosmologies, where the fundamental constants of physics, like the speed of light, were different in the early universe. If light traveled faster in cosmic youth, it could allow widely separated regions of space to coordinate their evolution, explaining the large-scale organization James Webb discovered without requiring impossible timescales. Modified gravity theorists like Dr. Sabine Hossenfelder are investigating whether gravitational physics itself works differently on cosmic scales or in extreme environments. If gravity was stronger or operated through additional dimensions in the early universe, structure formation could proceed much faster than general relativity predicts, naturally explaining the mature galaxies James Webb found. Even more radical are theories involving multiple universes or higher dimensional physics. Some models suggest our observable cosmos might be embedded in a larger multiverse structure, with matter and energy flowing between connected regions through mechanisms we do not yet understand. These scenarios could provide the additional organizational power needed to explain rapid cosmic evolution. Dr. Paul Frampton from the University of North Carolina has been exploring bouncing cosmologies, where dark energy cycles between expansion and contraction phases, creating periods of accelerated structure formation that could explain James Webb's observations. These models abandon the idea of a single Big Bang in favor of multiple cosmic epochs with different physical properties. The theoretical work is proceeding with unusual urgency because the observational evidence continues to mount faster than explanations can be developed. Each new James Webb discovery adds further constraints that eliminate more traditional explanations, forcing theorists toward increasingly exotic alternatives. What makes this theoretical revolution particularly significant is how it is happening across multiple sub-disciplines simultaneously. Cosmologists are revising their models of cosmic evolution. Particle physicists are questioning our understanding of fundamental constants. And astrophysicists are reconsidering the processes of stellar and galactic formation. The James Webb crisis is forcing a coordinated rethinking of physics itself. Some of the most promising new models involve what physicists call emergent gravity. The idea that gravitational attraction might not be a fundamental force, but rather an emergent property arising from more basic quantum mechanical processes. If gravity works differently than we thought, it could explain why cosmic structures form so much faster than our current theories predict. But these new theoretical frameworks are approaching a tipping point, where they might fundamentally change our understanding of time and space itself. Einstein's theory of relativity taught us that space and time are woven together into a single, unified fabric called spacetime, which can be stretched, warped, and curved by the presence of matter and energy. This profound understanding has been tested countless times and forms the very foundation of modern cosmology. But James Webb's discoveries are forcing physicists to question whether space-time itself might work differently than we have assumed, especially in the extreme conditions of the early universe. The problem is not just that galaxies formed faster than expected. It is that they formed in ways that seem to violate the principle of causality itself. Structure formation requires information to travel between different regions of space so they can coordinate their gravitational behavior. But in the early universe, many of the organized structures James Webb discovered are separated by distances that light had not had time to cross, making such coordination impossible under our current understanding of space-time. Dr. Lee Smolin from the Perimeter Institute has been exploring theories where time itself might be an emergent property, rather than a fundamental aspect of reality. In these models, what we experience as the flow of time could be an approximate description that breaks down under the extreme conditions of the early universe. If time worked differently, it could allow for processes that seem impossible under our current physics. Even more radical are theories suggesting that space might have additional, hidden dimensions that were accessible in the universe's youth, but became curled up and hidden as the universe evolved. These extra-dimensional models could provide pathways for information and energy to travel faster than the speed of light in our familiar three-dimensional space, explaining the impossible coordination James Webb observed. Some physicists are even investigating whether the speed of light itself might not be a constant throughout cosmic history. If light traveled faster in the early universe, it would allow widely separated regions to communicate and coordinate their evolution, naturally explaining the large-scale organization that formed too quickly under our current physics. Dr. Carlo Rovelli from the French National Center for Scientific Research has developed loop quantum gravity theories, where space-time itself is quantized, made up of discrete, indivisible units rather than being a continuous fabric. In these models, the very fabric of space-time might behave in strange and unpredictable ways under the extreme conditions of the early universe, allowing for structure formation processes that are impossible in the smooth, continuous spacetime of classical physics. The implications of these ideas reach far beyond cosmology and into the very nature of reality itself. If our understanding of time and space is fundamentally wrong, it affects everything from the foundations of quantum mechanics to the possibility of time travel. The James Webb discoveries might be showing us that the universe operates according to a deeper level of physics that we have not yet discovered. These space-time theories are all converging on a single, disturbing possibility that the Big Bang might not have been the beginning of everything after all. For nearly a century, the Big Bang has been more than just a scientific theory. It has been our culture's origin story, the ultimate answer to the profound question of where everything came from. But James Webb's discoveries are forcing us to confront the possibility that the Big Bang might not have been the beginning of everything, but rather just one event in a much larger, much older cosmic story that we are only now beginning to understand. The evidence is pointing toward a universe that was already organized and structured when the event we call the Big Bang occurred. The massive galaxies, the early heavy elements, and the coordinated large-scale structures that James Webb discovered all suggest that cosmic evolution did not start from a smooth, uniform, and simple beginning. Instead, they hint at a universe that inherited its organizational information from whatever came before. Dr. Anna Ijas from New York University has been developing models where the Big Bang emerges from the collapse and bounce of a previous universe. In these scenarios, the organized structures that James Webb observed could be the fossilized remnants of cosmic evolution that preceded our current phase of expansion. The universe might undergo infinite cycles of expansion, contraction, and rebirth, with each cycle preserving and building upon the information from the previous one. Even more revolutionary are theories suggesting that multiple universes might exist simultaneously, with matter and energy flowing between them through mechanisms we do not yet understand. If our observable cosmos is connected to a larger multiverse, it could explain where the organizational power for such rapid structure formation came from. It was simply borrowed from neighboring universes. Some physicists are exploring the possibility that the Big Bang was actually a phase transition rather than a creation event, just as water can transition from ice to liquid to vapor, while remaining the same fundamental substance. The universe might have transitioned from one physical state to another without actually beginning to exist. Dr. Abhay Ashtekar from Pennsylvania State University has developed loop quantum cosmology models where the Big Bang singularity is replaced by a big bounce, a transition from a contracting phase of cosmic evolution to our current expanding phase. In these models, the universe has no beginning and no end, but rather undergoes eternal cycles of expansion and contraction. The philosophical implications are staggering. If the Big Bang was not the beginning, then questions about what came before it become scientifically meaningful rather than just metaphysical speculation. The universe might be infinitely old, with our current expansion phase being just one chapter in an eternal story. This possibility challenges not just our cosmology, but our entire understanding of causation, existence, and the nature of reality itself. If the universe has always existed in some form, it changes how we think about everything, from the origins of the physical laws to the possibility of life having existed in previous cosmic cycles. The James Webb discoveries might be showing us that we are not the first chapter of cosmic evolution, but rather the latest chapter in an infinite book. The scientific revolution brewing in cosmology is not just about adjusting details or fine-tuning existing theories. James Webb's discoveries are approaching a critical threshold where the accumulated evidence might force the complete abandonment of our current cosmic origin story in favor of something entirely different. We are standing at the edge of a paradigm shift that could rival the Copernican revolution in its scope and its implications for human thought. The tipping point in science comes when anomalies can no longer be explained by modifying existing theories. In the history of science, this moment arrives when multiple, Independent lines of evidence all converge on the same conclusion that the fundamental assumptions underlying the accepted theory are simply wrong. The James Webb discoveries are rapidly approaching this critical mass of contradictory evidence. Dr. Subir Sarkar from Oxford University describes the current situation as a crisis of epic proportions in cosmology. The standard model of cosmic evolution requires increasingly exotic and elaborate modifications to accommodate each new James Webb observation. Dark energy must be more complex. Dark matter must behave differently. Inflation must work in ways we never imagined. And stellar physics must operate under a completely different set of rules in the early universe. The mathematical contortions required to save the Big Bang theory are becoming so elaborate that many physicists are questioning whether it is time to abandon the theory entirely, rather than continue patching it with increasingly implausible modifications. It is reaching the point where the cure is becoming worse than the disease. Major scientific institutions are beginning to acknowledge the severity of the crisis. The European Space Agency has approved funding for missions specifically designed to test alternative cosmological models. The National Science Foundation in the United States has created new funding categories for research into non-standard cosmologies. These institutional responses reflect a growing recognition that the James Webb discoveries represent more than just interesting anomalies. The convergence of evidence is accelerating. Every few months, new James Webb observations add to the pile of inexplicable data. The statistical probability that all these anomalies could be explained by measurement errors or theoretical oversights is approaching zero. The universe that James Webb is revealing simply does not match the universe that our theories predict. Historical precedent suggests that we are approaching the moment when the scientific community will be forced to choose between increasingly implausible explanations for the existing theory and revolutionary new models that naturally explain the observations. The geocentric Ptolemaic system of planetary motion required increasingly complex epicycles to match observations, until Copernicus proposed that the Sun, not the Earth, was the center of the solar system. We might be witnessing a similar moment in cosmology. The Big Bang theory is requiring increasingly complex modifications to match James Webb's observations. Alternative theories that seemed radical just a few years ago are beginning to look like natural and elegant explanations for what we are actually seeing. The next few years of James Webb observations will likely determine whether we are looking at the end of the Big Bang era in cosmology and the beginning of something completely new. The story of how the universe began is not just a scientific theory. It is the foundation of how we understand our place in existence itself. If James Webb's discoveries force us to abandon the Big Bang theory and embrace a completely different cosmic origin story, the implications will cascade through every aspect of human knowledge, from philosophy and religion to our most basic sense of meaning and purpose. Throughout history, changes in our cosmic story have triggered profound shifts in human consciousness. When Copernicus showed that the Earth was not the center of the universe, it did not just change astronomy, it revolutionized philosophy, religion, and humanity's sense of its own importance. When Darwin revealed that life evolved through natural selection rather than being specially created, it transformed not just biology, but our entire understanding of what it means to be human. The James Webb revolution promises to be even more fundamental. If the universe has always existed in some form, with no ultimate beginning, it challenges our most basic assumptions about causation, creation, and the nature of existence itself. The questions that have driven human inquiry for millennia. Why is there something rather than nothing? What came before the beginning? What is our cosmic purpose would need to be completely reframed. Dr. Carlo Rovelli from the French National Center for Scientific Research argues that major scientific revolutions always force us to reconstruct our understanding of reality from the ground up. The James Webb discoveries are not just challenging cosmology, they are challenging the conceptual frameworks we use to understand existence itself. If the universe operates according to a level of physics we have not yet discovered, with time and space working differently than we have assumed. It opens up possibilities we can barely imagine. Maybe consciousness plays a fundamental role in cosmic evolution. Maybe information is more fundamental than matter and energy. Maybe the universe is stranger and more wonderful than our current theories even allow us to suggest. The implications extend to the possibility of life itself. If rocky planets and complex chemistry emerged billions of years earlier than we previously thought, the universe might have been teeming with life when our own solar system was still just a distant possibility. We might not be among the first intelligent beings to contemplate the cosmos, but rather the latest in an unimaginably long chain of cosmic evolution. Even our understanding of death and time could be transformed. If the universe undergoes eternal cycles of expansion and contraction, with information being preserved across these cosmic phases, it raises profound questions about whether anything is ever truly lost. The James Webb discoveries might be showing us a universe where existence itself is eternal and indestructible. The psychological adjustment to a completely new cosmic story will be challenging. Humans have always needed origin stories to provide meaning and context for their lives. The Big Bang Theory, for all its scientific precision, also served as a modern creation myth that helped people understand their place in the cosmos. But perhaps the most profound implication is that the James Webb discoveries remind us of how much we still do not know. The universe continues to surprise us, revealing new mysteries just when we thought we had everything figured out. The greatest discovery might not be any specific new theory, but rather the humbling recognition that the cosmos is far stranger, more complex, and more wonderful than we ever imagined. The James Webb Space Telescope was built to confirm our understanding of cosmic origins. Instead, it might be showing us that the greatest adventures in understanding are still ahead of us, waiting to be discovered in the infinite mystery of existence itself. We set out to prove our cosmic origin story with the most powerful telescope ever built, expecting to find confirmation of everything we thought we knew about the universe. Instead, James Webb showed us galaxies that should not exist, stars that formed too quickly, and structures too organized for a universe in its youth. The telescope that was meant to be the ultimate witness to the Big Bang might instead be writing its obituary. The evidence is overwhelming and undeniable. Massive galaxies in the cosmic infancy, heavy elements that formed impossibly fast, rotation speeds that break the laws of physics, collision signatures that predate possible interactions, star formation rates beyond all theoretical limits, and planetary systems that assembled before their ingredients should have even existed. Each of these discoveries, taken alone, might be explained away, but together, they paint a consistent and damning picture of a universe that refuses to follow our rules. This is not just a crisis in cosmology. It is a revolution in our understanding of reality itself. The accumulated weight of James Webb's observations is forcing physicists to question not just when the universe began, but whether it had a beginning at all. We might be witnessing the end of the Big Bang era and the birth of a completely new cosmic story. The implications cascade through every aspect of human knowledge. If time and space work differently than we have assumed, if the universe has always existed in some form, if cosmic evolution operates according to a level of physics we have not yet discovered, then everything we thought we knew about existence needs to be reconsidered. The questions that have driven human inquiry for millennia must be completely reframed. But perhaps the most profound discovery is how much mystery remains. The universe continues to surprise us, revealing new wonders just when we thought we had everything figured out. The James Webb observations remind us that the cosmos is far stranger, more complex, and more wonderful than our theories suggest. The greatest scientific revolutions in history began with observations that did not fit the existing theories. Copernicus, Darwin, Einstein all started with pieces of evidence that forced humanity to reconstruct its understanding of reality from the ground up. The James Webb discoveries might represent the beginning of a similar revolution, one that will transform not just cosmology, but our entire conception of existence itself. We stand at the threshold of a new cosmic story, one that might reveal the universe to be eternal, infinite, and far more mysterious than we ever imagined. The telescope that was built to confirm our origin story might instead be opening the first chapter of an entirely new book of cosmic understanding. The greatest adventures in discovery are not behind us. They are waiting to be written in the light of ancient galaxies that refuse to follow our rules, in the spin of impossible stars, and in the organization of a universe that seems to have known exactly what it was doing from the very beginning. The story of how the universe came to be is not ending. It is just beginning to be told.